All right, people, let me know in the chats if I'm perfectly audible and visible to each and everyone. Welcome to Unacademy NEET English. If you have not subscribed to the channel yet, hit the subscribe button as soon as possible. Okay? And make sure you like this session. That's mandatory. Liking the session is mandatory. Let the people join and we are starting the session accordingly. Okay? What's up, people? What's up, people? Fire in the chats, everybody out there. Fire in the chats, everybody out there. Great, great. So, people, today we have this particular session that is we say speed revision. Okay, speed revision, all high weightage chapters, and this is for ultra legends only. Those students who have the capability to change the entire game at the end moment, I say this session is for those students. Okay, so I say over here, guys, everybody out there, make sure you smash the like button. Okay, I want you guys to make it 500 plus right now. Everybody out there, everybody out there. Okay, so people, quickly tell your friends we are starting this particular session, which is a must watch. Okay, so all the high weightage chapters we will be discussing in this one. This will be the speed revision, and the question is in how much time we are supposed to finish this particular session. We say 2 hours, something like that. In next 2 hours we will be completing. My speed will be a bit fast. Okay, so you have to be very much I would say attentive in the class. Okay, just keep your 100%, give your 100% in this particular session so that you understand each and every single thing whatever I say. Okay, and when it comes to basically writing the notes, I suggest you don't have to make the notes over here. If you have a good speed, you can make the notes, but I will be sharing the notes in the Telegram channel also. Okay, so let me mention that Telegram channel over here. When it comes to the Telegram channel, that is, I say t.me/unacademy. Unacademy, we say NEET English. Unacademy NEET English. You can join this Telegram channel. Okay, so I will be sharing the notes over here. So everybody out there, guys, now shall we start the session? I want everybody of you to tell me in the chats with the fire emojis. Everybody out there, everyone means everyone, everyone means everyone. Okay, great. Smash the like button. I want all the people out there. Okay, because marking the attendance is mandatory. Everyone means everyone. Everyone means everyone. Great. Now let's start this particular session without wasting the further time. Now see. So the first chapter that we are starting with is, we say, electrostatics. Okay, we will be starting with electrostatics. Okay, so when it comes to the electrostatics, my dear friends, everybody out there, we say 4 to 5 questions you can expect from this particular chapter. That means 20 marks. So this is the high weightage chapter, extremely high weightage chapter. So the first topic that we need to exactly focus on in electrostatics, that's Coulomb's law. Let's suppose I say I have got a charge over here, another charge over here. This is a positive charge and this is one more positive charge over here. Okay, and I say, sir, these two positive charges will apply force on each other. These two positive charges will apply force on each other. How much is the force between the two charges? We say, sir, K Q1 Q2 divided by R square. Everybody knows it. Okay, and when it comes to the value of K, we say it is 1 by 4 pi epsilon naught. Okay, and this epsilon naught is permittivity of free space. What is the value of epsilon naught? That is 8.85 into 10 raised power minus 12 Coulomb square upon Newton meter square. And if you put the value over here, so K will come out to be 9 into 10 raised power 9. We say Newton meter square upon Coulomb square. So if you have got the two charges, they apply the force on each other. Okay, this will repel this charge, this will repel this charge. How much will be that force? K Q1 Q2 by R square. Okay, this is the first topic in Coulomb's law. This is the first topic in Coulomb's law. Next we have over here, listen to me very carefully, that is equilibrium position. I want all of you to basically be attentive over here. Next is equilibrium position. My dear friends, I will be discussing all the high weightage chapters. Okay, every single chapter which is having the high weightage will be discussed in this one. Now guys, let's suppose we have got a charge over here that is plus Q. We have got one more charge over here that is n times of Q. And if I ask you the question, where should we place the third charge so that net force on it is 0? I am saying place the third charge over here at this distance x. We say, sir, net force will be 0. Now the question is, how much will be this x? You say, sir, this x will be r upon under root of n plus 1. Okay, n means over here. Okay, if I say this is 9 times of Q, 9Q. So in that case, we say, sir, 9. N in this case is 9. Next we have, if we have got a positive charge over here, okay, and if we have got a negative charge over here, this is plus Q and this is minus Q over here. Okay, we say, my dear friends, if I ask you where is the equilibrium position, where should we place the third charge so that net force on it is 0? So we say this is the position and that is what we call x. That's what we call x over here. Okay, and my dear friends, this x in this case will be r upon under root of n minus 1. This is the formula we use in that case in which we have got the two charges which are opposite in nature, okay, which are opposite in nature. Next, my dear friends, next, my dear friends, my dear friends, the third question that may be asked from this portion is, if you have got this charge, okay. Now in this case, I am asking you, what is the value of that third charge? How much is Q naught? That is minus n times of Q upon under root of n plus 1 whole square. This will be the value of that third charge, okay. Next we have over here, guys, if we have got a ring over here, everybody listen to me very carefully. Sir, charge on this ring is, we say, sir, plus Q. Radius of this ring is capital R. And I am asking you, how much is the electric field at x distance because of the ring? So we say at x distance, electric field will be simply, that is KQX, x is the distance, okay, divided by R square plus x square whole raised power 3 by 2. Okay, capital R is the radius of the ring over here. Everybody out there. Now if I say, sir, at center we say, sir, value of x is equal to 0. So if you put 0 over here, we say complete electric field will be 0 at the center. At the center of the ring, we say electric field will be 0. Next, and if somebody asks you, what is the graph between electric field versus R? What is the graph between electric field versus X in case of a ring? What is the graph between electric field versus X in case of a ring? So we say this will be the graph in that case. Okay. Here you have to remember one thing. That is nothing but we say, see, this point is, we say, sir, where electric field is maximum. And electric field will be maximum at x is equal to plus r by root 2 and x is equal to minus r by root 2. So in case of the ring, electric field is maximum at plus r by root 2 and minus r by root 2. Okay. Next. Now guys, we say, sir, electric field due to a segment of ring. My dear friends, if we have got, let's suppose, this segment of a ring over here, okay. So we say we have got a positive charge on this ring, okay, on this segment. Segment means some part of the ring. If you join this with one end, this point, if you join this with another end. Now guys, this is what we call the radius. Angle between these two is theta. And if somebody asks you how much is the electric field at this point, we say it is simply K 2K lambda by R sine of theta by 2. So electric field due to this segment of ring at this point is, we say, 2K lambda by R sine of theta by 2. Next, if I say, sir, if you have got a semicircle, so we say in case of semicircle, theta is equal to 180 degrees. We say theta is equal to 180 degrees. Now guys, if I ask you to tell me the electric field at this point because of this segment, because of this semicircle, you'll directly say, sir, this will be, sir, 2k lambda divided by r. So you have to basically put theta is equal to 180 over here, then you will get 2k lambda by r, 2k lambda by r, as simple as that. Okay, next we have got a chord over here. Okay, this is the chord over here. So because of this chord, the electric field at this point, this is radius, this will be radius, this is what we call the chord. Electric field at this point because of the chord is simply root 2k lambda divided by r, where r is basically the radius, where r is the radius. Okay, next we have, my dear friends, if you have seen a rod something like this, this is a rod over here. Okay, and charge on the rod is, we say, sir, q. Now at r distance if we go, now join this point, we have to find the electric field at this point. So join this point with one end, join this point with another end. This is what we call theta 1 and this is what we call theta 2. So because of this finite rod, we have to find the electric field at this point. So this electric field will be simply, that is k lambda by r. R is the distance where we have to find the electric field. Then we say sine of theta 1 plus sine of theta 2. Then we say plus cos of theta 1 minus cos of theta 2. This will be the electric field. This will be the electric field because of this finite rod at this particular point. Okay. Next. Now guys, if we talk about the equatorial position, means the point which is exactly at the midpoint. Okay, like in the previous case, this was the arbitrary point, means general point. Now if I take this point, this will be the point which is exactly in between. Okay, so we say in case of this equatorial point, electric field is simply, that is 2k lambda by r sine of theta. 2k lambda by r sine of theta. When the point is exactly at the midway, that's what we call the perpendicular bisector or equatorial point. Okay. Now guys, if you have the infinitely long rod, like we have this infinitely long rod, it is going till infinity from one end and it is going till infinity from the another end. Because of this infinitely long rod, electric field at r distance is simply 2k lambda by r, 2k lambda by r, as simple as that, Are you able to understand everything? Guys, let me know in the chats, everybody out there, let me know in the chats. Everybody out there. Is this crystalline clear? We have to keep the speed high, guys. Then only we can complete all those chapters. Approximately we will be completing 12 13 chapters, like 14 to 15 chapters in this one. Okay, we'll be revising 14 to 15 chapters in this one approximately. Everybody. Okay, make sure you like this particular session, everybody out there. So this is the electric field because of the infinitely long rod. Electric field because of the infinitely long rod. Okay. Electric field because of the infinitely long rod. So that is 2k lambda by r. Now guys, if you have got semi-infinite, what does that mean? Means if we talk about this rod, okay, it is going till infinity from one end, but other end is over here which is finite. So we say this is semi-infinite, means it is going till infinity from one end, other end is finite. And if I am asking find the electric field at r distance because of this rod, you say that will be root 2k lambda by r. Okay, because of the semi-infinite. Because of infinite, how much is it? We say 2k lambda by r. Next we have got over here electric flux. What is the concept of electric flux? Everybody, guys, if let's suppose I have got a sheet over here, I have an area, and we say, sir, electric field lines are crossing this area over here. Okay, I have an area, electric field lines are crossing the area. So we say flux is being produced. So we say number of field lines crossing the surface perpendicularly is flux. If I say number of field lines are crossing over here this area, we say flux will be produced in that case. So flux is produced here. And what is the formula of flux? Sir, E dot S, okay, or E dot A, you simply say. So we can simply say EA cos of theta, EA cos of theta. Flux is proportional to electric field. More electric field lines are over here, we say flux will be more, because then more field lines will cross. We say more bigger is the area, we say more field lines will cross, so flux will be basically large. Okay, flux is simply how many number of field lines are crossing the surface, as simple as that. Okay, now here we have to talk about the Gauss law. Here we have to talk about the Gauss law. What does Gauss law say? It states that flux through any closed surface is charge divided by Q by epsilon naught. Guys, listen to me very carefully. If we have got a closed surface over here, that is cylinder, and we have placed a charge inside the cylinder, we say because of this charge, electric field lines will exactly come out, something like this, something like this. Okay, now these field lines are basically crossing the surface of the cylinder. So we say here electric flux is being produced, flux is being produced. And if I ask you how much is the value of that flux, you say, sir, that is Q by epsilon naught. Q is the charge in that case that you have placed inside, divided by epsilon naught. Can I say here also how much will be the flux in this particular case? We say, sir, here also flux will be Q divided by epsilon naught. Why? Because charge is inside the closed surface. Okay, next we have got over here. This is very important from the NEET perspective. I want you guys to keep your mind in here. Direct question have been asked many times in your NEET as well as JEE from this particular concept. What is that? We say over here, guys, electric field due to a hollow sphere or metal sphere, conducting. This is a conducting sphere. I have got a sphere over here. Charge is present on the surface of the sphere. Okay, we say it will produce electric field. Now its radius is capital R. My question to you is, because of this sphere, electric field at outside point will be how much? You say, sir, that is KQ divided by R square. Q is what? Q is the charge on the sphere. R is the distance at which you are supposed to find the electric field outside. Okay. Now guys, if I talk about the sphere, if I talk about the surface, if you keep on reducing the small r at surface, can I say this small r becomes equal to the capital R? Yes. So at surface, electric field will be KQ by capital R square. Okay. Because of the hollow sphere. In case of hollow sphere, we say charge is present on the surface only. Inside it is hollow. Inside charge is zero. Okay, and if inside charge is zero, we say electric field inside will be zero, as simple as that. Let's take a look at its graph. If we have got a sphere over here, we say, my dear friends, the graph will be simply inside electric field is zero, so graph will be on this line. Outside, E is inversely proportional to R square, so outside it will be rectangular hyperbola. Outside it will be rectangular hyperbola. It is outside. Okay. Next we have got a solid sphere. Solid sphere means non-conducting sphere. In the question it may be also given that it is a non-conducting sphere. That is a solid sphere. Okay. Now guys, in case of solid sphere, we say, sir, charge is present inside. Charge is present inside. Okay. Inside. So my dear friends, over here we have to find the electric field because of this sphere outside at small r distance, on the surface capital R distance, inside at small r distance. Small r is variable. Okay, for outside point small r is bigger, for inside point small r is smaller. Okay, now at outside point, if I say electric field due to the solid sphere, what will you say? That is KQ divided by R square. This will be outside. Okay, same as hollow sphere. And if I say at surface, value of small r is equal to capital R. If you keep on reducing the small r, once you reach the surface, at surface small r becomes equal to capital R. So we say then it will be KQ divided by capital R square. This will be, we say, electric field due to a solid sphere on the surface. And inside, guys, here, inside charge is present. Charge inside is not zero in this case. So we say electric field inside will be simply, that is KQ divided by R cube, where capital R is the radius of the sphere and small r is the distance where you have to find the electric field inside. Small r is the distance where you have to find the electric field inside. Hey, tell me in the chats, is this crystalline clear? Is this crystalline clear to each and everyone? Let me know in the chats, everybody, guys. Is this crystalline clear? Everybody with the fire emojis, with the fire emojis. And if somebody asks you to make the graph between electric field versus R in case of a solid sphere, you say, sir, graph will be something like this. Okay. So we say this is the graph inside. This is the graph inside. Inside we say electric field is directly proportional to R. Why? Because you can see over here, inside electric field is directly proportional to R. And outside electric field is inversely proportional to R square. So from here, this is basically till surface radius R, and outside we say this will be inversely proportional to R square. Outside it is inversely proportional to R square. Next, my dear friends, guys, this graph is very important. This was basically asked. This is very important. Electric field due to a solid sphere on its surface. Due to a solid sphere, graph between E versus R in case of a solid sphere. Next we have got over here, that is we say electric field due to infinitely large non-conducting sheet. Infinitely large non-conducting sheet. If you have got a non-conducting sheet over here, okay, so we say charge is present on this sheet, so it will produce electric field. So at point P, because of this sheet, how much is electric field? We say simply it is sigma by 2 epsilon naught. It is simply sigma by 2 epsilon naught. Okay, this sigma divided by 2 epsilon naught. Sigma means charge per unit area. Sigma is Q divided by A. Okay, charge per unit area in this particular case. Next, if you have got a conducting sheet, conducting plate or sheet, see how does conducting sheet actually look like. You have got one sheet over here. Another sheet is something like this. Positive charge is present onto this particular sheet and positive charge is present over here. Positive charge is present over here. And in between there is no charge. So this is what we call the conducting sheet. Now we have to find the electric field because of the conducting sheet. That will be simply sigma by epsilon naught. That is simply sigma by epsilon naught. And in terms of charge, we say Q by 2A epsilon naught. Q will be the charge on this sheet. Q will be the charge on this sheet. Is this crystalline clear? Everybody in the chats. Now, next. Motion of a charged particle in uniform electric field. Guys, if I say I have got an electric field over here, okay, this is the electric field. And in this electric field, I am placing a charge, okay, whose mass is M, which has got the mass M. Whenever we place the charge inside the electric field, we say it will experience the force, okay? We say it will experience the force. Force will act on it. And that force is simply Q times of E. Q is the charge, E is the electric field in which you have placed the charge, okay? And guys, if I say force is acting on this charge, we say it will have acceleration. Okay, if force acts on somebody, we say it will have acceleration. So acceleration of this charge is simply QE divided by M. Acceleration of this charge is simply QE divided by M. Okay. Now guys, if I ask you how much is its velocity, if it is now moving, how much is its velocity after some time? Its velocity will be simply QE divided by M into T. Now, if I ask you how much displacement it will cover after some time, displacement will be simply 1 by 2 QE by M into T square. 1 by 2 QE by M into T square. Okay. And if somebody asks you how much is the momentum of this charge, you say, sir, momentum of this charge will be QET. Q is the charge, E is the electric field, T is the time. And if somebody asks you how much is the kinetic energy of this charge which is placed in the electric field, okay, that is Q square, E square, T square divided by 2M, M into X. Q is the charge, E is the electric field, M is the mass of the charge, M is the mass of the charge, and we say X is the displacement it has covered, okay. Next, my dear friends, charged particle projected in the electric field perpendicularly. If you have got, my dear friends, electric field something like this, this is the electric field which we have got over here, okay. And in this electric field, you are sending a charge something like this with a velocity u. My dear friends, here we say because of this electric field, force will act on it in the upward direction, in the same direction as the direction of electric field. Now, this charge was supposed to go straight, but because of the force, it will follow this particular path, okay? It will be pulled in the upward direction. So let's suppose it leaves here with a velocity v. And this theta is what we call the deviation. Theta or alpha is what we call the deviation. Let's call this as alpha. This alpha is the deviation produced over here. How much it got deviated from the horizontal? So this deviation is simply tan inverse of QED. What is Q? Q is the charge, E is the electric field, D is the width of the electric field, in how much width electric field is present, divided by mu square. What is m? M is the mass of the charge, u is the velocity of the charge, initial velocity. So this will be the deviation in this particular case. Next. Okay, let's talk about the dipole. Okay, guys, everybody of you must be familiar with the dipole. What is a dipole? Whenever you have got a positive, negative charge and positive charge, two equal and opposite charges, when they are separated by some distance, it is called electric dipole. So here this is dipole. Now if I ask you how much is the electric dipole at an angle theta from, okay, now guys, see, if this is a dipole, we know, sir, a dipole has got a dipole moment, which is what we call P. And this dipole moment is always from negative charge to positive charge. And this dipole moment is, we say, sir, charge multiplied by distance between them, Q into D. Okay. Now, because of this dipole, we have to find the electric field at this point at x distance from the dipole, which is at an angle of theta over here. Now, this is the electric field at this point because of the dipole. That is Kp by x cube under root of 3 cos square theta plus 1. Kp by x cube under root of 3 cos square theta plus 1. This is the electric field because of the dipole at this general point. Now, if I say, guys, I am taking this point. This point is what we call the axial point, electric field because of the dipole on its axis. Because this is the point which lies on the axis of the dipole. Here, electric field will be simply 2kp divided by x cube. 2kp divided by x cube. Okay. This is the electric field because of the dipole on its axis. Next, we say electric field due to a dipole on the perpendicular bisector. What is that? If you have got a dipole over here, okay, so we say electric field you have to find at this point. This is what we call perpendicular bisector. This is the axial point, this is the perpendicular bisector. Here it will be simply minus kp by x cube. Minus represents the direction will be in the backward direction. Minus kp by x cube. On its axis, it will be how much? Twice kp by x cube. Here it will be minus kp by x cube, okay, because of the dipole on its perpendicular bisector. Okay. Now one more important concept. If let's suppose you have got an electric field over here. Okay. And in this electric field, you have placed a dipole. Guys, you have placed a dipole. This is negative charge. This is positive charge. Remember, guys, whenever you place a dipole in an electric field, we say it will try to rotate. Torque will be produced over here. Okay. And that torque is simply Pe sine theta. P is the dipole moment of this dipole, that is from negative charge to positive charge. E is the electric field, and theta is the angle between P and E. So whenever you place a dipole in an external electric field, we say torque will be produced on that dipole, and this is the value of that torque. And we said this torque is simply P cross E. This tau is simply P cross E. Because B sine theta is A cross B. P sine theta is P cross E. Okay. Now one more point. Electrostatic potential energy stored in a dipole in uniform electric field. If let's suppose you have got an electric field over here. Okay. This is the electric field. And in this electric field you have placed, let's suppose, a dipole. Okay. Now listen to me very carefully. If you rotate the dipole, if we rotate the dipole, by rotating the dipole, you will have to do the work done over here. You will have to do the work done over here in rotating the dipole. In rotating the dipole, you will have to do the work done. Okay? And because of that work done, we say potential energy will be stored in the dipole. So we can write work done by external force is equal to change in potential energy. So the work done you use in here to rotate the dipole, because of that potential energy will be stored in this particular case. Is this clear? Let me know in the chats, everybody out there. Is this crystalline clear? Everyone means everyone. Guys, if you have not liked the session yet, I want you guys to like the session as soon as possible. Liking the session is mandatory. Everybody out there. Liking the session is mandatory. Okay, I want you guys to make the likes 1000 plus as soon as possible. Everyone. Great. So now we say because of the external work done, potential energy will be changed. The potential energy of the dipole will be changed. Okay. Now guys, if I ask you how much is the potential energy stored in the dipole if you rotate it by theta, this will be the potential energy of the dipole. That is minus Pe cos theta, or you can also say minus P dot E. This is the potential energy of this dipole in this electric field we have got over here. Okay. Next, an important topic, potential due to a hollow or a solid sphere. Okay, first we will talk about the hollow sphere. Guys, if let's suppose we have the hollow sphere over here. Charge is present on the surface of the hollow sphere. This is the surface of the charge, or surface of the sphere. We have to find the potential because of this sphere outside, at outside point. That will be simply KQ divided by, we say R, KQ divided by R. Okay, because of this hollow sphere. Okay. So this is the potential because of hollow sphere at outside point, KQ by R. Now if I ask you what is the potential at the surface, you will simply say, sir, potential at the surface will be KQ divided by capital R. Because at surface, we say small r is equal to capital R. And when it comes to inside, this is the inside point from the center till this inside point at small r distance. We say inside, we say potential will be simply that is KQ divided by capital R. Whatever is the potential on the surface, same will be inside. Whatever is the potential on surface, same will be inside. Okay. Whatever is the potential on the surface, same will be inside. Great, great, great. Now guys, see, and if somebody asks you to make the graph in this particular case, guys, inside, see, when it comes to inside, K is constant, Q is constant, R is constant. So this is the whole inside potential is constant. So on the still surface, it is constant. So we say graph will be from this is center. From center to surface, potential is constant. So it is parallel to x-axis. And then outside it is inversely proportional to R, so it will be a rectangular hyperbola. It will be a rectangular hyperbola. Keep that thing in your mind. Next, potential due to a solid sphere. Potential due to a solid sphere. Guys, if you have got a sphere over here, okay, which is solid, means charge is present inside the solid sphere. You have to find the potential because of this outside, on the surface and inside. Outside it will be simply that is KQ divided by small r. Small r is the outside distance. On the surface it will be simply KQ by capital R. And when it comes to inside, guys, here charge is present inside. We say inside here potential will be KQ divided by 2r cube. Capital R is the radius. Then we have multiplied by 3r square minus small r square. This is the potential inside the solid sphere. And when it comes to the center, at center exactly, this is the potential at center, that is 3 by 2 KQ by R. Because of the solid sphere, potential at the center is 3 by 2 kq by r, 3 by 2 kq by r. Okay. Next, if somebody asks you what is the graph over here between potential versus, we say, sir, r, potential versus r, the graph will be simply that will be this one and something like this. At center it is highest, that is 3 by 2 kq by r. On the surface means r is equal to capital R. We say on surface it is kq by r. And outside it is inversely proportional to small r. Outside it is inversely proportional to small r. That's the reason we have got the graph something like this, Okay. Next chapter, let's revise this particular chapter, that is chapter 2, capacitors. Everybody over here. Okay. An important concept in the capacitors, what is that? If you have got n capacitors over here, and you join these n capacitors to form a big capacitor, okay? Now guys, in this particular case, if I say, what is the charge of the big capacitor Q? What is the capacitance of the big capacitor? Potential of the big capacitor, radius of the big capacitor, charge on the big capacitor. Directly you have to remember these values. Charge on the big capacitor will be simply n times of Q. What is Q? Small q. Small q is the charge on smaller capacitor. So if you join smaller capacitors to form a big capacitor, so charge on big capacitor will be simply n times of Q. Okay. And when it comes to the radius of big capacitor, we say simply it will be n raised power 1 by 3 into R. Okay, where R is the radius of the smaller capacitor. And my dear friends, if I ask you C dash, the capacitance of the big capacitor, it is n raised power 1 by 3 into C. What is n? We say n means number of capacitors over here. Okay, this is the capacitance of big capacitor. And we say, what is potential of big capacitor? This, it will be n raised power 2 by 3 into V. V is the, we say, potential of the smaller capacitor over here. Okay, okay. Next. Now we have got parallel plate capacitors. Guys, so whenever we place the two plates parallel to each other, okay, if I say positive charge is on this plate, negative charge is on this plate, this is what we call parallel plate capacitor. If you have got two, capacitor is a device which stores the energy. So we say this is the device which stores the energy. Here, if you have got two plates, means this is a parallel plate capacitor. Okay. Now the question is, how much is the capacitance of the parallel plate capacitor? You say simply it is epsilon naught A by D. Okay. This is the capacitance of the parallel plate capacitor. Guys, we say capacitor is a device which stores the energy. Okay. Capacitor is a device which stores the energy. Now, this capacitor may be having the capacity, how much energy you can store in the capacitor. That is the capacity of the capacitor. More is the capacity, more is its capacitance. Less is the capacity, less is its capacitance. So we say how much is the capacitance of this capacitor? Epsilon naught A by D. A is the area of the plates, D is the distance between the plates. Okay. Next. If I say, guys, how much energy you can store inside this capacitor? We say energy stored in the capacitor is simply, that is Q square by 2C. This is in terms of charge and capacitance. Q is the charge on the capacitor, C is the capacitance. In terms of capacitance and voltage, it will be simply 1 by 2 CV square. In terms of capacitance and voltage, it is 1 by 2 CV square. Okay. And in terms of charge and voltage, it is 1 by 2 QV. All of these formulas are basically the, we say, energy stored in the capacitor. Okay. Is energy stored in the capacitor. Next, force between. Now guys, listen to me very carefully. If I say I have got this plate, force, charge on this plate is positive, charge on another plate is negative. We say this positive plate will attract this negative plate. This negative plate will attract this positive plate with a force F. So how much is that force? This is the force. That is Q square upon 2A epsilon naught. This is the force between the plates of a parallel plate capacitor. Q square upon 2a epsilon naught. Or you can also write in terms of sigma, that is sigma square into A divided by 2 epsilon naught. Sigma square into A divided by 2 epsilon naught. Okay. This is also the force in terms of sigma. This is in terms of charge. Okay. Next. Guys, this is important. This is important. I'll mention it over here. Okay. See. If I say I have got a plates over here, this is a parallel plate capacitor. Okay. And in this I am placing a dielectric. Dielectric is a material. Like you have got conductors, you have got insulators. Okay. So same is the dielectric. Dielectric is the material that we are placing over here. Okay. Now guys, listen to me very carefully. When it comes to the dielectric, we say, because when you place the dielectric in between the plates, okay, we say positive charge of this plate will attract the negative charge of the dielectric, will attract negative charge. And negative charge of this plate will attract the positive charge of the dielectric. So in dielectric, negative charge is occupied something like this, positive charge is occupied something like this. And this is what we call Qi. That is induced charge induced inside the dielectric. And if somebody asks you how much is the value of this induced charge, that is Q. Q is the charge on plates into 1 minus 1 by K. K is the dielectric constant of this dielectric. Every dielectric has a dielectric constant. And if somebody asks you how much is the induced charge density, that is sigma I. Induced charge density, okay, charge per unit area, that will be simply sigma into 1 minus 1 by K. Sigma into 1 minus 1 by K. Okay. Sigma into 1 minus 1 by K. This is the induced charge density. Okay. Next. Okay. Guys, if you have got, this is the series combination of dielectrics. If let's suppose you have got two plates over here. This is positively charged plate. This is negatively charged plate. And you have placed a dielectric in between. The width of the dielectric is T. Its dielectric constant is K. Distance between the plates is D. And if somebody asks you how much will be the capacitance of this capacitor in which this dielectric is placed, that is C is equal to epsilon naught A D minus T. D is the width between the two plates. T is the width of this dielectric, then plus T by K. This is the capacitance of this capacitor in which you have placed this dielectric of width T. And let me know in the chats if this is getting crystal and clear to each and everyone. Is this clear? Is this clear, guys? Everyone means everyone. Guys, let me know in the chats. Okay. Great. Okay. Now, next we have got over here. Okay. This one. See. Guys, before this, I just want to tell you one more thing. What is that? Let's suppose if you have got the two plates, something like this. This is one plate and this is another plate. Okay, this is one plate and this is, we say, another plate. And here we have placed one dielectric, 2 and 3, and we have, say, 4. So dielectric constant of this is K1, K2, K3, and this is K4. Its width is D1, D2, D3, and D4. In this case, I am asking you to find the net capacitance of this capacitor. You say C is equal to epsilon naught A upon. Then you say D1 by K1 plus d2 by k2, you say d2 by k2, then plus d3 by k3, then plus d4 by k4. Keep this thing in your mind. Keep this thing in your mind. Next, this is also what we call the series combination of the dielectrics. If the dielectrics are placed in series, okay. Next, if you have got, let's suppose something like this, okay. This is what we call here parallel combination of dielectrics. If you have got two plates, okay, in between the two plates, this is the first dielectric, second, and this is third. These are the dielectrics placed in parallel. Okay, its dielectric constant is K1, K2, K3. Separation between the plates is D. And this width over here is A1, A2, A3. Now its capacitance, if somebody asks you how much is the capacitance of this capacitor, epsilon naught by D, A1, K1, plus A2, K2, plus A3, K3. This is the capacitance of this capacitor. Okay. 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 One more thing. If you have got the three capacitors in series, their equivalent capacitance will be 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. And if you have got the capacitors in parallel, their equivalent capacitance will be simply C1 plus C2 plus C3. Okay. Next, let's move on to the next chapter, that is current electricity. Guys, everybody of you know that, sir, what is electric current? Electric current is simply the flow of charge. Okay. How much, if you have got a conductor over here, how much charge is flowing? The more charge is flowing over here, the more current will be produced. Okay. So current is simply Q by T, charge upon time. Okay. And when it comes to the average current, we write average current as delta Q by delta T. Okay. And when it comes to the instantaneous current, we say it is simply dQ by dt. dQ by dt. Average current is delta Q by delta T. Okay. Instantaneous current is dQ by dt. Next. Guys, here, we say given, listen to me very carefully. If charge is given, you are supposed to find instantaneous current. What are you supposed to do? We say you will do I instantaneous is equal to dQ by dt. So we say you will differentiate at that point of time. Now, if charge is given, and you have to find average current, okay, I have shown you in the marathons or in the, we say in the marathons only, I have shown you tons of questions on this pattern. If charge is given, you are supposed to find average current. You will be using this formula, delta Q by delta T. Okay. And if current is given, you are supposed to find the average current. In that case, you will be using this formula, integration I dt upon integration dt. And if current is given, you are supposed to find charge. You will be using this formula, that is Q is equal to integration of I dt. Q is equal to integration of I dt. This is the formula which you will be using in that case. Okay. This is the formula which you will be using in that case. Next, drift velocity. What does drift velocity actually mean? What does drift velocity actually mean? Guys, we say if you have got a conductor over here, and in this conductor you have these electrons which are flowing. Okay. My dear friends, listen to me very carefully. We say, if there is a conductor, there are so many free electrons over here, and you connect a battery here. Okay. If you connect a battery over here which has got the potential difference V, we say, in this particular case, sir, this battery will set up the electric field. Because of this electric field, these electric force acts on these electrons in the opposite direction. So they will start flowing. When they start flowing, so means they will gain some velocity. That is what we call drift velocity. So drift velocity is that velocity with which electrons flow in a conductor. And how much is the formula of drift velocity? This is the formula. V is equal to E by m into tau. E is the charge on an electron. E is the electric field, this electric field which is being set up because of the battery. M is the mass of an electron and tau is the time or relaxation time over here. So this is the drift velocity. Next concept we have got over here. Now, if somebody asks you guys, if these electrons flow over here, we say current will be produced. Now, what is the relation between drift velocity and current? So this is the relation between drift velocity and current. So that is I is equal to NEAVD. N is the number of free electrons per unit volume of the cross section, and VD is the drift velocity of these electrons. As simple as that, as simple as that. Next we have got over here, that is Ohm's law. Ohm's law says if you have got a conductor, you connect a battery over here, okay? So we say because of this battery, electric field will be set up, so these electrons will flow, okay? Now, when these electrons flow, we say current is being produced. Now, if I say more is the potential difference, more electric field will be set up, more force will act on the electrons, more will be the current. So can I say, sir, potential difference is directly proportional to the current? Yes, sir. Now, replacing this proportionality, we say V is equal to Ri. So this is what we call Ohm's law. Ohm's law says that current is directly proportional to, we say, potential difference. Potential difference is directly proportional to the current, okay? And resistance is constant. Now, guys, we say over here, if I make the graph between V versus I, we say, let's suppose the graph is this. Remember, in this particular case, directly I want you guys to remember, if I ask you to find the slope over here, you say, sir, slope in this case will be simply resistance. Okay? If I ask you, guys, V versus I graph is given. I'm asking you find the slope of this graph. You'll find slope tan theta. That will be resistance of this wire. Okay? So if I ask you to find the resistance, means you will find the slope. And if IV graph is given, in this case, we say, sir, slope is inversely proportional to resistance. If you find the slope of this graph, that will be inversely proportional to the resistance. Okay? Okay. I hope I have proven this already. Now, question over here is, compare the resistance of the wire A, wire B, and wire C. Guys, see, when it comes to this wire C, it has got less slope. This has got more slope and this has got more slope. I can simply say slope of A is greater than slope of B is greater than slope of C. Now, come over here. We say, sir, slope is directly proportional to resistance. If slope is directly proportional to the resistance, we say resistance of A is greater than resistance of B is greater than resistance of C. As simple as that. This is the logic that we actually use over here. Now, the concept of resistance. We say, sir, resistance is basically opposition to the current. Okay? We say resistance is directly proportional to the length. If you have got a conductor over here, if its length is large, we say resistance will be large. And resistance is inversely proportional to the area of cross section. So we can say R is equal to rho L by A, where rho is the resistivity. This is the formula for resistance. Resistance is simply opposition to the current. Midpoint potential, important. Mark this as important. Mark this as important. Okay. Now, guys, listen to me very carefully. When it comes to the midpoint potential, guys, see. I have got over here, let's suppose this one. I have got one resistance over here, okay? I have got another resistance over here, and I have got one more resistance over here. The potential here is V1, resistance is R1. Potential here is V2, resistance is R2. Potential here is V3, resistance is R3. And this is the point which is what we call the midpoint. And this has got the potential Vm. That is common potential. If I say you have to find this midpoint potential, is there any formula? Yes, that is V1 by R1 plus V2 by R2 plus V3 by R3 upon 1 by R1 plus 1 by R2 plus 1 by R3. So this is what we call the common potential or the midpoint potential. If these are given, okay, and you have to find the potential of this point, you can find by using this method. This is very important. With the help of this formula, I have shown many bigger problems to solve in just seconds. Okay. Okay, now, okay, this series combination of cells. If you have got cells connected in series, okay, E1, E2, E3, E4, these are in series. Resistance R1. This is, by the way, the internal resistance of the cell or battery. Cell means battery. Battery cell has got its internal resistance, okay. So R1 is the resistance of battery E1. R2 is the resistance of cell E2. Now here, if you have to find the net EMF, so this is the EMF, potential difference of this, EMF of this. If you have to find the net EMF in series, it will be simply E1 plus E2 plus E3 plus E4 up to En. And net resistance of all of these internal resistances will be R1 plus R2 plus R3 up to Rn. Okay, as simple as that. And in case of parallel combination, guys, remember, if you have got the cells in parallel, E1, E2, R1, R2, their equivalent resist EMF or net EMF, I'll write over here. This is equal to V net EMF. That is E1 by R1 plus E2 by R2 upon 1 by R1 plus 1 by R2. This is how do you find it over here. This is the net EMF in case of parallel. And equivalent resistance will be simply, if you have to find the equivalent resistance of these two, it will be R1, R2 upon R1 plus R2 upon R1 plus R2. As simple as that. As simple as that. Next. Okay. Now, if let's suppose we say n identical batteries are connected in parallel. Okay. E, R. Okay. These are the identical cells connected in parallel. N identical cells connected in parallel. And here, if you have to find the equivalent in EMF, net EMF in this case, that will be simply E. That will be simply E. N, for N identical cells, it is simply E. R equivalent will be R by N. One more was here, that is mixed grouping. If you have N cells in series, 1, 2, 3, 4, up to N, and M times in parallel, here it is M times in parallel. Here, in this combination, this is what we call mixed grouping. Here the cells are connected in series as well as in parallel. And if somebody asks you how much is the net EMF in this case, that will be N times of E. And R equivalent in this case will be equivalent of all of these resistances will be NR by M, NR by M, NR by M. Is this clear? Is this clear? Okay. Is this clear? Let me know in the chats, guys. Everybody out there with the fire emoji. Everybody. Okay. Great. So this is basically what we call the mixed grouping. Let's move on to the next one. Now the concept of galvanometer. Okay. We say, sir, galvanometer is a device which is used to detect the current. Okay. It also measures the small amount of currents. Galvanometer is a device which measures the current. It detects the current. It also measures the small amount of currents. Now see, how do we make the galvanometer? See, if let's suppose, okay, now conversion of galvanometer into a meter. Now see, galvanometer is a device which is used to detect the current and it measures the currents. But it measures the small currents. It measures the small currents. If you have to measure the large current, you have to use the ammeter. So now the question is, how do we convert the galvanometer into a meter? See, if we have got a galvanometer over here, so we connect a shunt resistance in parallel to it. When we connect a resistance in parallel to galvanometer, it becomes the ammeter. Remember it directly. If I say now I is the current which enters this particular setup, Now guys, we say Ig will be the current, that is current in the galvanometer will flow through the galvanometer. Now how much is remaining? Remaining will be I minus Ig, that will flow through this shunt resistance. And in this case, you will be asked to find how much amount of shunt resistance should we connect so that we can set up a good galvanometer, or its range will be increased or something like that. So this is the value of shunt. Ig into G. Ig is the current in the galvanometer. G is the resistance of the galvanometer divided by I minus Ig. Okay, so this is the value of the shunt which you connect in parallel over here so that you form the ammeter. Next, conversion of voltmeter and galvanometer as a voltmeter. Now we say galvanometer is also a device which measures the voltage or potential difference. So here we have to convert the galvanometer into the voltmeter. We have to convert the galvanometer into the voltmeter. Okay. Now guys, listen to me very carefully. We say we have got the galvanometer over here. If we connect a shunt resistance in series, it becomes the voltmeter. It becomes the voltmeter. It becomes the voltmeter. Okay. If we connect a shunt resistance in series, it becomes the voltmeter. As simple as that. As simple as that. So now, if I ask you how much is the value of shunt over here, you say this shunt will be V divided by Ig minus we say G. V by Ig minus we say G. Okay, Ig is the current in the galvanometer, G is the resistance of the galvanometer, V is the voltage across this. As simple as that. Magnetic effects of current. See, guys, from current electricity portion, you can expect 4 to 5 questions. From electrostatics portion also, you can expect 4 to 5 questions. Here, you can expect 2 to 3 questions. Okay, minimum you can expect 2 questions from this. Okay. Now listen to me very carefully. Listen to me very carefully. The first is we say Biot-Savart's law. What does it say? If we have got a wire over here in which current I is flowing, okay, we say, sir, this wire in which current I is flowing, it will produce the magnetic field around it. Remember it directly. If I say, my dear friends, I take a small element dl over here, okay. So at r distance, we have to find the magnetic field because of this current element dl. So Biot-Savart's law tells us the current because of the current element, not because of the whole wire. Keep that thing in your mind. So because of this current element IDL, we have to find the magnetic field at r distance, which is at angle theta. So that will be mu naught by 4 pi. This is constant over here. Mu naught is the permeability of free space. Then we have IDL. IDL is the current element. Sine theta. Theta is the angle between R and IDL divided by R square. And its vector form is, that is dB is equal to mu naught by 4 pi IDL cross R divided by R cube. This is the magnetic field because of the small current element at R distance in vector form, which gives you magnitude as well as direction. This was asked in NEET 2020. This expression. And how do you find the direction of magnetic field? See, place your thumb along the direction of current, curl your fingers over here. If it is curling, if it is going inwards, so magnetic field here will be inwards. As simple as that. As simple as that. Okay. Next. We have got magnetic field due to a finite wire. Magnetic field due to a finite wire. If let's suppose you have got a wire over here, okay, and in this wire we say, sir, current I is flowing. Current I is flowing in this wire. Now, my dear friends, we have to find the magnetic field at point P because of this finite wire. Whole wire now we have to find. Previously, we calculated the magnetic field because of the current element. Now we'll be calculating because of the whole wire at r distance. Join this point with one end, join this point with another end. This is theta 1, this is theta 2. So magnetic field at this point P will be mu naught by I by 4 pi r. R is the distance. Then we say sine of theta 1 plus sine of theta 2. This is the magnetic field because of the finite wire at r distance. Okay. And here magnetic field will be inwards. How to find the direction? Place your thumb along the direction of current, curl your fingers here, that will be inwards. Next, magnetic field due to the infinite wire. If you have got a wire which is going till infinity from lower side and infinity from the upper side, so at r distance, magnetic field will be simply B is equal to mu naught I divided by 2 pi r. Mu naught I divided by 2 pi r. This is the magnetic field because of the infinitely long wire, and graph between B and R is B is inversely proportional to R. Next, magnetic field because of the semi-infinite wire. If you have got a semi-infinite wire over here, means which is going till infinity from one end only. So at R distance, magnetic field will be B is equal to mu naught I divided by 4 pi R. B is equal to mu naught I divided by 4 pi R. Okay, if you have got, let's suppose, a ring, okay, and in this ring current I is flowing, its radius is capital R, we know, sir, it will also produce the magnetic field. We know, sir, it will also produce the magnetic field. So at x distance, how much magnetic field it will produce? Mu naught I is the current in the wire, into R square. R is the radius of this ring, divided by 2 into R square plus x square whole raised power 3 by 2. This is the magnetic field because of this ring at R distance, at x distance, this x distance. And at center, can we say x is equal to 0? So if you put x is equal to 0 over here and solve it, it will come out to be mu naught I by 2r. So at center, magnetic field because of this ring in which current I is flowing is mu naught I by 2r. Okay. Now see, just a second, guys. Guys, I hope you have liked the session, okay? Because liking the session is mandatory. Everybody out there, mark the attendance. Like the session as soon as possible. Now, guys, magnetic field due to a segment of ring. If you have got a segment of ring over here, some part of the ring, not the whole ring, and in which current I is flowing, join this point with one end, join this point with another end, we say this angle is theta. So magnetic field will be mu naught I by 2r, theta divided by 2 pi. Mu naught I by 2r, theta divided by 2 pi. Okay? And this is the general formula that you can. Ampere's circuital law. What is Ampere's circuital law? Ampere's circuital law, we say it is simply used to find the magnetic field. Guys, we say if we have got a wire over here, okay, in which current I is flowing, this is infinitely long. At small r distance, we have to find the magnetic field. We know because of the Biot-Savart's law, we can use that also to find the magnetic field. But by using the Ampere's circuital law also, we can basically find the magnetic field. Like, what is this? That is closed line integral BDL. Take a small line integral over here, that is DL. And we say, let's suppose magnetic field because of this wire at over here is B. So closed line integral BDL is equal to mu naught times of I enclosed. What is I enclosed? If you have to find the magnetic field at this point because of this wire, you take a loop over here, you draw a loop which is crossing this point. This loop is what we call the Ampere's loop. Okay, so we say this point is loop is what we call Ampere's loop. So we say you write mu naught times of I enclosed. That current which is in the Ampere's loop, you have to mention that current. Okay. Now, how do we exactly find it? Let me show you over here. You can take the magnetic field out. This is integration of BdL. Integration of, we say, sir, dl is equal to mu naught times of I. Now, if you integrate dl of this means you will get the circumference of this circle over here. That is 2 pi r. So B into 2 pi r. Integration of dl will be 2 pi r is equal to mu naught times of I. So how much will be the magnetic field? B is equal to mu naught into I divided by 2 pi r. So this was the magnetic field because of the infinitely long wire. And we calculated this magnetic field using Ampere's law, not the Biot-Savart's law. Magnetic force. Now guys, see, if a charge is placed in a magnetic field, given some velocity, force will act on it. That is what we call the magnetic force. Like over here, if you have got a charge over here, this charge is basically placed in a magnetic field. This magnetic field is inward. This is an inward magnetic field. Okay. And this charge is placed in this inward magnetic field. So it is moving with a velocity v. We say force will act on this magnetic field. How much is that? That is qvb sine theta. Q is the charge, v is the velocity, b is the magnetic field, and sine theta. Theta is the angle between velocity and magnetic field over here. Now guys, if I say theta, if I say I have got a charge over here, we say magnetic field is in the forward direction. We say charge is moving with a velocity v in the same direction over here. Can I say in this particular case, sir, force will be 0? Why? qvb sine 0. Here, angle between velocity and magnetic field is 0. So force in this case will be 0. And if theta is equal to 180 degrees, okay, magnetic field is, let's suppose magnetic field is backward. Velocity of the charge is forward. So we say here also magnetic force will be 0. So guys, remember one thing. Whenever you place a charge in a magnetic field and some velocity is given to that charge, we say force will act on that charge. That force will be magnetic force, and that is equal to qvb sine theta. Now, the third case is, if let's suppose you have a charge over here, you are giving some velocity to this charge, that is v. Magnetic field here is inwards. This is the inward magnetic field. Guys, listen to me very carefully. We say in this particular case, don't you think that velocity and magnetic field, they are perpendicular? How? See, velocity is forward, magnetic field is inward, so angle is 90. Whenever a charge enters the magnetic field perpendicularly, in that case, charge moves in a circular path. And if somebody asks you, what is the radius of that charge? That is mv divided by qb. M is the mass of that charge, v is the velocity with which it is moving, q is the charge, b is the magnetic field. And if somebody asks you, in how much time it will complete one cycle, that is the time period. So that is 2 pi m by qb. Okay. And if somebody asks you, what is the radius of that circle in terms of kinetic energy, that will be under root of 2m kinetic energy divided by qb. This is the radius in terms of kinetic energy. And this is the radius in terms of velocity. And if somebody asks you, find this velocity of the charge also, that is v is equal to r/b divided by m. r/b divided by m. I hope this is also clear. This is also clear. Okay. Now, one more thing. Force on a wire placed in a magnetic field. Guys, listen to me very carefully. If you have got an inward magnetic field over here, okay, and in this inward magnetic field, you are placing a wire in which current I is flowing. I is the current flowing in the wire. Listen to me very carefully. We say whenever you place a wire or a rod inside a magnetic field, okay, in which current I is flowing, its length is L, we say force will act on this rod. And that force is what we call the magnetic force. Okay. And guys, listen to me very carefully. Here, the force will be equal to, that is, F is equal to ILB sine theta. ILB sine theta. What is I? I is the current in the wire. L is the length of the wire. B is, we say, sir, magnetic field. B is, we say, sir, magnetic field. So whenever you place a wire from now onwards in a magnetic field in which current is flowing, we say force will act on that wire. Next, guys, one more thing. If let's suppose I say I have got two wires over here. Current I1 is flowing in this wire, and you have got another wire which has got length L. This is infinitely long. Current I2 is on this wire. Now we say they apply the force on each other. Whenever you have the two parallel wires in which current is flowing, we say they apply force on each other. Here, if I say how much is the force on this wire 2 because of the wire 1, that is simply F is equal to mu naught I1 I2 divided by 2 pi r into L, divided by 2 pi r into L. I1 is the current in this wire, I2 is the current in this wire, R is the radius distance between the two wires, and L is the length of this wire. And if somebody asks you find force per unit length, force on its unit length, this is the force on the entire wire. Now force on its unit length will be simply F by L, total force by total length, that is mu naught I1 I2 by 2 pi r into L divided by L will cancel, so this will be force per unit length in that case. Okay, now one more point, magnetic dipole. Listen to me very carefully, guys. When it comes to the magnetic dipole, like you have seen electric dipole, similarly we have got the magnetic dipole. A bar magnet out there in the market is considered to be as magnetic dipole. Like if you take a bar magnet over here, okay, this bar magnet has got south pole and it has got north pole, and this has got, we say, sir, minus M, this is, we say, sir, plus M. This minus M and plus M, this is the pole strength. This is the pole strength. Okay, how stronger these poles are. And like here you have the dipole moment, here also you have the dipole moment. M is equal to M into L. M is the pole strength, L is the distance between the two poles. L is the distance between the two poles. As simple as that. Okay. And this magnetic dipole moment is from minus M to plus M, from south pole to north pole. Okay. Now listen to me very carefully. My dear friends, if you have got a magnetic dipole, okay, if you have got a magnetic dipole, I will say M, okay, and this is minus M over here, this is plus M over here. Now you are placed this, you have this magnetic dipole over here. Sir, magnetic dipole will also create the magnetic field, okay. So because of this magnetic dipole, first we'll find the magnetic field at this point, which is an arbitrary point. That is mu naught by 4 pi M by r cube. If I say at r distance, M by r cube. M is the magnetic dipole moment of this one. Then we say 1 plus 3 cos square theta. Theta is this angle. Theta is this angle. Okay. And if I say the magnetic field because of this magnetic dipole on its axis at this point, that will be twice mu naught I by 4 pi M by r cube. And if I say at perpendicular bisector equatorial point, here this is arbitrary point, this is actual point, this is perpendicular bisector, that will be mu naught by 4 pi M by r cube. As simple as that. As simple as that. Okay. Next. Okay, if let's suppose you have got the magnetic field over here, and in this magnetic field you have placed this magnetic dipole. Okay, so whenever we place the magnetic dipole in a magnetic field, we say here also it will rotate, torque will be produced. So that torque is equal to mb sine of theta. M is the dipole moment, that is from minus M to plus M. B is the magnetic field, and theta is the angle between M and B. M and B. M and B. Okay. And like over here, this is the potential energy of the magnetic dipole. Potential energy of the magnetic dipole. Like if you have got magnetic field over here, and in this magnetic field you have placed the magnetic dipole. So whenever you place the magnetic dipole in the external magnetic field, we say here, then if you rotate, by rotating, we say potential energy will be stored in this dipole. How much is that potential energy? That is minus mb cos theta. Okay, m is the dipole moment, b is the magnetic field, and theta is the angle between m and b. Or you can also say it is minus m dot b, because m dot b is mb cos theta, a dot b is ab cos theta. Okay. Okay. Next. Okay. Let's move on to this concept. That is the reflection of light. Let's revise this ray optics. Okay. Ray optics. High weightage chapter, and it's a big chapter. Hey guys, is this clear till over here? Let me know in the chats, everybody out there. Is this clear till over here? Let me know in the chats. Everyone means everyone. Guys, if you have not liked the session yet, like it as soon as possible, okay? Smash the like button. Now see, let's revise this particular chapter over here. That is, we say a ray optics. Everybody over here. So first is basically reflection of light. What does reflection of light mean? If I say there is a light over here which is incident, this is the reflecting surface. There is a light over here which is incident on the surface, and it gets reflected over here. So we say this is incident ray and this is reflected ray. And if we draw a line over here, this is what we call normal. We say in this case, this angle of I is equal to angle of R. Angle of incidence is equal to angle of reflection. And this angle between reflecting surface and incident ray will also be equal to angle between reflected ray and reflecting surface. These two are also equal. This is what we call the reflection of light. Okay. Reflection of light. Okay. And we say the incident ray, reflected ray, and the normal all lie in the same plane. Next. Guys, if I say deviation by plane mirror, let's suppose you have got a plane mirror over here. This is a reflecting surface. And we say, my dear friends, an incident ray is falling on this. If the incident ray is falling on this, we say, sir, it gets reflected something like this. My dear friends, look at this. This is the normal over here. We say if there was no reflecting surface, it would have gone straight something like this. Can I say this will be the deviation in that case? How much it got deviated from the original path? This deviation is, we say, 180 minus 2 theta. Directly, I want you guys to remember it. and we say deviation by two plane mirrors. If we have got one plane mirror, if we have got another plane mirror, theta is the angle between the two plane mirrors. I say in this particular case, my dear friends, if I say this is the incident ray which falls on mirror M1, then it gets reflected, falls on the mirror M2, then it gets once again reflected, and this is the final ray. So now this will be the deviation, angle between original ray and final ray. In this case, deviation will be 360 minus 2 theta. So this will be theta over here, 360 minus 2 theta. As simple as that. Next. Listen to me very carefully. What is object? What is object? Guys, we say it is defined as the point of intersection of the incident rays. Guys, listen to me very carefully. You might have studied, you might have seen or observed one thing. What is that? If let's suppose you have got a mirror over here. In front of the mirror, you have a person. This is what we call object. We know its image will be formed inside the mirror. This is what we call image. Now, what is the technical definition of this? What is the physical? In physics, how do we define it? We say if this is a mirror, in front of the mirror, you have got the object. We say incident rays will leave from the object over here. Okay. And we say, my dear friends, listen to me very carefully. We say, see, if this is the object, now incident rays will leave from the object. This is the mirror. They get reflected something like this, these rays. So if you extend these rays, the point where they meet, that is what we call the image. And here we consider this as virtual image. Why? Because these rays, we say, do not actually meet. These rays do not actually meet over here. Okay. So we say they appear to meet in this particular case. Like over here, if I say incident ray is something like this, we say, my dear friends, in this particular case, if you extend these incident rays, they appear to meet over here, and this will be virtual object. This is the real object, because in reality, these two rays are meeting over here. So here, the two rays are meeting virtually. Same is the case over here. We say, if light rays are basically reflected something like this, so we say if you extend the reflected rays, the point where they meet is what we call image. So it is the point of intersection of reflected rays. Now here you have got a mirror. So this will be, we say, sir, real image. Incident ray, reflected ray. Incident ray, reflected ray. The point where they meet is what we call the reflected ray. You can ignore this also. So what is important in this case is let's suppose this one. Find the minimum size of the plane mirror to see the full image of an observer. Guys, see, we say over here, this is an observer. Over here, this is an observer. Or we say, you have got the object over here. My dear friends, listen to me very carefully. And you have got a mirror over here. In front of the mirror, you have placed what? We say object. So we say behind the mirror, its image will be formed. In front of the mirror, you have the object. Behind the mirror, its image will be formed. Now I say, how much amount, what is the size of the mirror that is required to see its image? So that is h divided by 2. H is the height of the object. H divided by 2 means this much is the size of the mirror which is required to see the size of the object. That is h by 2. As simple as that. Directly, if I say you have got the object over here, its image is formed over here. Now I am saying how much should be the size of the mirror required to see the complete image. That is h by 2. That's it. You have to basically keep this thing in your mind. Okay. Now one more important concept over here. The relation between velocity of object and image. Guys, see, if let's suppose you have got an object over here. You have got a mirror over here. We know, sir, in front of the mirror, we place the object. Everybody listen to me very carefully. And its image will be formed over here. This is object, its image will be formed over here. Now, if I say this object is moving with certain velocity, what is the velocity of the image? With what speed image is moving? This will be Vi is equal to 2 times of Vm, where Vm is the speed of mirror. Let's suppose mirror is also moving with some speed. Minus Vo. Vo is the speed of object. This will be the velocity of image in that case. You have to remember it. Okay. Okay. Now guys, if I say object is moving parallel to the mirror, like something like this. If I say object is moving something like this, we say in this case, image will be also moving parallel to the mirror. So here, velocity of image will be equal to the velocity of object. Velocity of image will be equal to the velocity of the object. Okay, next. Number of images formed by the plane mirrors. Here, you have to directly remember one thing. See. If you have got a mirror over here, M1, if you have got mirror over here, M2. Let's suppose the object is placed over here. Guys, listen to me very carefully. This object is an angle alpha. We say its image will be formed over here, I1 in this mirror M1. At what angle? Also at an angle alpha. Okay? As simple as that. Now, this will behave like an object for mirror M2. Now, this behaves like an object for mirror M2. What is the angular distance between I1 and M2? That is alpha plus this angle is theta. Angle between this one and this one. So we say it's the image of this object is made over here, that is I2 at what angle? Alpha plus theta. Similarly, now this object image will behave like an object for this mirror. So this is at what angle? Alpha plus theta, that is alpha plus 2 theta. So next image will be formed at alpha plus 2 theta. Alpha plus 2 theta. Okay. So we say in this particular case, if somebody asks you, how many number of images can be formed by using two mirrors? That will be simply, if M is coming out to be an integer, listen to me very carefully. First we find M. Okay. First we find M. So how do we exactly find M? We say over here, listen to me very carefully. Guys, if I say this is theta over here, if I say you have to find the value of M, you can find the value of M as 360 divided by theta. 360 divided by theta. So now, if M comes out to be an integer, in that case, we say, sir, if M is even, number of images will be M minus 1. And if M comes out to be odd, we say in that case, object is at, and if object is at angle bisector, number of images will be M minus 1. If object is not at angle bisector, number of images will be M. Okay. So this here, I hope you have joined my marathon session, because over there I have explained this in complete detail. Here I will just revise it and move on. If you are getting any sort of confusion in understanding this, then I request you go back to my marathon, okay, complete physics part 2. Over there you can watch this and you will get to understand every single point about this. Okay. Now what I need to explain over here, that is mirror formula. One second. This is done. Okay, let's move on to this one. Mirror formula and sign conventions. What does mirror formula actually say? That is 1 by V plus 1 by U plus 1 by F. What is U? U is the position of the object, V is the position of the image, F is basically the focal length. F is the focal length. Okay? F is the focal length. So my dear friends, we say this formula helps us to find the position of the object, to find the position of the image, to find the focal length also. As simple as that. Okay, so this is what we call the mirror formula. And sign conventions in this case. We say take that direction as positive in which incident ray is moving along the principal axis. We have to consider that direction as positive in which incident ray is moving. in which incident ray is moving. Like I say, if I have got a mirror over here, I am taking the spherical mirror, I am placing the ray or object over here. So this is the direction of incident ray. Okay, like I'll use this particular color. If I say this is the mirror over here, this is the mirror over here. In front of the mirror, I am placing the object. We say this will be the direction of incident rays, because incident rays always leave from the object. So this will be the positive direction, and this is, we say, sir, negative side. So that's what I'm trying to say. The direction, take that direction as positive, which is the direction of incident rays, Now, my dear friends, before this, I just want to tell you something. What is that? Come over here. Yeah, spherical mirrors. Guys, see. I'll explain spherical mirrors in five minutes. Let's suppose we have got a mirror over here. We have got a complete sphere. If we cut a sphere over here, it will become something like this bowl. This inner side is what we call concave side. Outer side is what we call the convex side. Okay. Now, if we polish from outer side, then it becomes concave mirror. And if we polish from inner side, it becomes convex mirror. Here reflection takes place from front side. Here reflection takes place from back side. As simple as that. Now, if let's suppose we'll place a mirror over here, this is a concave mirror. Now we'll basically take a line. This is the line which passes through the center. This is what we call the principal axis. And this point is what we call the pole. Now, this will be basically center of curvature. Okay, if you complete this circle over here, this will be the center of the circle. Here we call it center of curvature. And this is what we call the radius of curvature R. As simple as that. And this is what we call the incident ray over here. And between center of curvature and pole, there is, we say, sir, focus. Okay, and focus is, we say, R by 2. You guys have to remember this. Focus is, we say, R by 2. Okay, and here also I explained this mirror formula. What is this mirror formula? Mirror formula means, if let's suppose you have got a mirror over here. In front of the mirror, you are placing an object. So at what distance this object is, that is, we say, sir, U. So we say its image will be formed somewhere around over here. That will be the position of the object. So with the help of this formula, you can find the position of the object, position of the image, and so on. Okay, and focal length also. Next, we say magnification. Magnification. It is defined as the height of image upon the height of object. If you have to find the magnification, so we say it is height of image divided by height of object. As simple as that. How much magnified the image has become, how much bigger the image is as compared to the size of object. So what is the formula for magnification in terms of, we say, V and U? This is minus V by U. This is also magnification. Next, in terms of F and V, this is the formula of magnification in terms of F and V. F is focal length, U is the position of object. In terms of F and, this is F and U. In terms of F and V, F minus V divided by F, this is also the magnification. One more thing I just want to tell you over here. What is that? Image formation. Let's suppose, guys, you have got a concave mirror. Image formation in case of concave mirror. Let's suppose you have got a mirror over here. Listen to me very carefully. You have got a mirror over here. Now, guys, this is center of curvature. This is focus and this is pole. If object is placed over here, directly remember, guys, if object is placed over here, if object is placed beyond 2F, beyond center of curvature, then in this case, guys, see, one incident ray will leave something like this and it passes something like this. Another incident ray will leave something like this, it passes something like this. The point where they meet is what we call the image, because the point where reflected rays meet is what we call image. The point where incident rays meet is what we call the object. So here in this case, image will be formed between F and 2F. You have to remember this. In case of concave mirror, if object is placed beyond 2F, then image will be formed between F and 2F. Image is formed between F and 2F. Image will be real. What is real image? Real image is where reflected rays actually meet. Okay? Image will be inverted, image will be diminished. Inverted will be what? Inverted is what? We say upside down. This is This is not inverted. This is erect. This is inverted, upside down. And diminished. Diminished means small, smaller than the object. It is smaller than object. Next, if object is placed between F and 2F, this is 2F, center of curvature, this is F. If object is placed over here, image will be formed beyond 2F. Image will be formed beyond 2F. So here, image is formed beyond 2F, and it will be real, inverted, and magnified. Real, inverted, and magnified. Very important, all of these cases. Next, these are all the important cases, guys. Next, if object is between focus and pole, you have got this mirror over here. Object is between, this is pole and this is focus. Now this is object. In this particular case, we say image will be formed behind the mirror. Image is formed as virtual. Virtual image means where reflected rays appear to meet. They actually do not meet, they appear to meet. Okay. And image will be erect. Erect will be this. And magnified means bigger. Okay. Next, image formation in case of, we say, sir, convex mirrors. If object is near to the mirror, guys, convex mirror means this one, in which it is polished from inner side. In this case, pole will be from the, focus is from this side, center of curvature is from this side. Now we do not place the object from this side. Why? Because it is polished from this side. We have to place the object from that side in which there is a reflecting surface. Here there are two cases only. If object is placed near to the mirror, this is near to the mirror. In this particular case, image is formed virtual. Here image is formed virtual, erect, diminished, between focus and pole. Between focus and pole. Between focus and pole. Is this clear till over here? Let me know, guys, in the chats if this is clear. Okay. I hope this is clear, guys. I hope this is clear. I hope this is clear. Now, if object is placed near to the mirror, guys, see in this particular case, if I have got a mirror over here, this is the mirror. Okay. So we say if object is placed near to the mirror, in this case, image is formed virtual. Okay. Virtual over here. Erect. Erect means something like this. And diminished. Diminished is small. Diminished is small. And it is between pole and focus. This is focus and this is pole. Next case in this is if object is placed at very far distance. If object is placed at very far distance. You have got mirror over here. Okay. Object is placed at infinity, at very far distance. In this case, we say here image is formed erect. We say it is very small. It is virtual, erect, and very small. Okay. Guys, you have to remember all of these cases. And image is formed at focus. Okay. These are the two cases in case of convex mirrors. Mirror formula also we are done. Okay. With the help of the mirror formula, you can find V, you can find U, and you can find F. Magnification also we are done. Magnification means how much bigger is the size of image as compared to the size of object. Okay. That is done. That is done. Okay. Now, this is the velocity of image in case of spherical mirrors. See. If let's suppose I have got an object which is moving with a velocity VO. Okay. Velocity of mirror is, let's suppose, VM. And in this case, we have to find the velocity of the image. Guys, listen to me very carefully. We say velocity of image with respect to the mirror will be minus m square. M is what? M is the magnification. Then velocity of object into velocity of object. Okay. And we say 99.9% of our cases, we say velocity of mirror would be 0. Velocity of mirror would be 0. We consider mirror at rest in 99.9% cases. Okay. Okay. So if that is the case, we say, you can also write it something like this. Velocity of image with respect to the mirror is v square by u square into, we say, sir, velocity of object with respect to the mirror, because magnification is v square by u square. Now, power of mirror. Power of mirror is defined as the ability to converge or diverge the light rays. How much ability the mirror, spherical mirrors have to converge or diverge the light rays. Okay, so that is defined as the power of mirror. So how do we write it? P is equal to -1 upon f. F is the focal length. This is in meters, which is equal to -100 upon f. This is in centimeters. As simple as that. Okay. Okay. Refraction of light. Let's suppose, my dear friends, we have a surface over here. The light basically falls onto the surface, and from the upper side, it has got medium 1. From the lower side, it has got medium 2. Like you have got air over here, you have got water over here. So there are two mediums. So when light falls onto the surface, if it is reflected in the same medium, it is what we call the reflection. But if it enters into another medium, then we say it is what we call refraction. Refraction of light is entering the light from one medium to another medium. Now, if light is reflected in the same medium, in that case, we say we say velocity of light. Okay, we say this is wavelength over here, lambda. This is frequency. We say all of these will remain same. If they enter the another medium, we say in that case velocity will change v2, wavelength will change lambda2, and we say frequency will be f over here. Frequency remains same even if it enters the another medium. Next, law of refraction. What does law of refraction mean? See, it says that, guys, if light enters from one medium to another medium, it is what we call the refraction. Okay. Now, in this particular case, we say incident ray, reflected ray, refracted ray. This is the incident ray and this is the refracted ray. And normal all lie in the same plane. All lie in the same plane. Next we say Snell's law over here. Snell's law says that mu I into sin I. Mu I is the refractive index of that medium in which incident rays are present. And mu R is the refractive index of that medium in which refracted rays are present. So we say mu I into sin I. It will be equal to mu R into sin R. This is what we call the Snell's law. So in law of refraction, we have got two laws. Incident ray, refracted ray, and normal all lie in the same plane. Second in Snell's law, that is mu I into sin I. I is the angle of incidence, R is the angle of refraction. Okay. Now let's talk about the prism. Let's suppose we have got a prism over here. Okay. You might have seen prism in your schools. Okay. This is the prism. So this is what we call the angle of prism. Guys. We say in this particular case, if the incident ray falls onto this prism, listen to me very carefully. It enters the prism. So we say prism is another medium. Okay. So here it is in air. The light ray was in air. That is rarer medium. And here it is denser medium. Okay. Remember one thing. Whenever the light enters from rarer medium to denser medium, it is bent, we say, towards the normal. And if the light ray enters from denser to rarer, it is bent away from the normal. So in this particular case, if it moves from rarer to denser, it is bent towards the normal. This is the normal on the surface. And then it again comes out. It moves from denser to rarer. We say, sir, then it goes reflected, something like this, refracted. So this is normal. It moves away from the normal. Okay, this is the normal here. Guys, listen to me very carefully. This is the angle of prism. This is angle of incidence I. Okay, A is called apex angle or angle of prism. I is the angle of incidence on surface 1. Consider this as surface 1. R is the angle of refraction on surface 1, R1. R2 is the angle of incidence. This R2 is the angle of incidence on surface 2. And E is the angle of emergence. E is the angle of emergence. This angle, or we say angle of refraction on the surface 2, on this surface 2. Okay. Now, if I say there was no prism over here, this incident ray would have gone straight, something like this. We say in this case, it got deviated because of the prism this much. And this is what we call deviation. This is what we call deviation. Now, remember the formulas directly over here. If somebody asks you how much is the deviation, that is I plus E minus A. Angle of incidence, angle of emergence, angle of prism. A is equal to R1 plus R2. Okay. Apply the Snell's law on surface 1. Mu of air into sin I is equal to mu. That is mu of, see, if we apply the Snell's law on surface 1, that is mu I, mu of air, because here it is air, into sine of I, is equal to mu of this, that is refractive index of this prism, into sine of R1. You can similarly apply the Snell's law in the surface 2 also. Okay. And one more thing. This is the graph between deviation and angle of incidence. This is the graph between deviation and angle of incidence in case of prism. So it is something like this. So clearly you can see over here, this is what we call minimum deviation and this is what we call maximum deviation. Okay. And this minimum deviation, when is the minimum deviation? Deviation is what? How much the incident ray got deviated from its original path. So for minimum deviation, we say minimum deviation is when angle of incidence is equal to angle of emergence. So when this angle of incidence becomes equal to the angle of emergence, we say in that case deviation is minimum. In that case deviation is minimum. And when R1 is equal to R2 is equal to R. Here you can say R is equal to A by 2 and deviation will come out to be 2I minus A. So for minimum deviation, deviation is how much? 2I minus A. Keep this thing in your mind. Okay. So this is the refractive index of a prism. If somebody asks you to find the refractive index of the prism at minimum deviation, what will you say? Mu is equal to sine of A plus delta minimum by 2 divided by delta, this is sorry, sine of A by 2. This is sine of A by 2. Okay. I hope this is clear and crystal to each and everyone. Okay. Refraction at spherical surfaces. Refraction at spherical surfaces. Let's suppose you have got a spherical surface over here. Okay, this is a spherical surface. Previously, we studied about the refraction at plane surfaces. Now we are discussing the refraction at spherical surfaces. Guys, see, if let's suppose I have an object over here, from the object incident ray will leave. Okay, so after this here, we say it will be refracted something like this. It will be refracted something like this. So guys, we say this is object. Let's suppose this is image. Can I say this is U in this case? The position where object is placed, that is U. And the position where image is placed, that is, we say, sir, V. Okay. And this is the let's suppose this is medium 1 over here. And this is medium 2 over here. The refractive index of this medium is mu I. The refractive index of this medium is mu R. Mu I is the refractive index of that medium in which incident rays are present. Mu R is the refractive index of that medium in which refracted rays are present. Okay. Now guys, here also we have the formula. What is that? Mu R by mu V, mu R by V minus mu I by U is equal to mu R minus I divided by R. Okay. Okay. So with the help of this formula, you can find U, position of object, position of image, and we say, sir, R is the radius of curvature over here. So with the help of this formula, like you had the mirror formula previously, here you have got this formula. And magnification in this case will be M is equal to V by mu R. u by mu I. Okay, and one more formula, velocity of image with respect to the spherical mirrors. So that is, in this particular case, let me basically take it over here. It is simply velocity of image with respect to the spherical mirror is equal to v square by u square, mu I by mu r, velocity of object with respect to the spherical mirrors. You can use this formula in order to find the velocity of image. Next. Okay, then you have got the lenses. We say a lens is made up of two surfaces in which refraction takes place. Okay, like you have got one surface, another surface. So if you join these two surfaces, this is what we call the lens. And more specifically, this is biconvex lens. Okay, this has got radius of curvature R1, this has got radius of curvature R2. Now, if you have to make the concave lens, this will be the concave lens. This will be the concave lens. This is what we call the biconcave lens. Okay, so this has got radius of curvature R, this is R2 and R1. Okay, so basically the lens is made up of two spherical surfaces. When two spherical surfaces meet, we say lens is made, lens is formed. Next, lens maker's formula. So we say similarly here we have the lens maker's formula, which helps us to find the focal length, position of object, position of image. Like you have mirror formula, here you have got this lens maker's formula. 1 by v minus 1 by u is equal to mu l by mu s. What is mu l? Mu l is the refractive index of the lens. Keep that thing in your mind. Okay. And mu s is the refractive index of surrounding. Minus 1 by r1 plus minus 1 by r2. R1 is the radius of curvature of one surface. R2 is the radius of curvature of another surface. Now you can also write 1 by f is equal to mu l by mu s minus 1, 1 by r, 1 minus 1 by r2. Okay. Okay, optical instruments. See, let's focus on the optical instruments. So we have first the simple microscope. So we say, where do we actually use these microscopes? See, we say, sir, I use microscope in order to see small things large. That's for what we use microscopes. If there is a small, very small thing which I am not able to see my normal eyes, what do I use? I use microscope, and that's what we call the simple microscope. Okay. So we say the work of a simple microscope is to magnify the things, to make us see small things large. Okay, that is the work of a small microscope. Now listen to me very carefully. Directly I'll come on to over here. See, this is the lens. You might have seen the simple microscope, like you have that lens, something like that. That is what we call the simple microscope. Okay, so if this is the object over here, you are not able to see, this is your eye, you are not able to see this object with your eyes. So you will place the lens in between the object and the eyes. Okay, so this lens will basically magnify the object. It will make it bigger. It will look bigger to your eyes now. So how much will be the magnification? That is d by f. What is this d? D is the least distance of distinct vision. What is d? Guys, see. If I say I have to see this particular object, at what is the minimum distance I should place it? Sir, minimum, if I place it close to my eyes, I am not able to see it. Minimum distance will be 25 centimeter. So 25 centimeter will be D, that is least distance of distinct vision, divided by F. F is, you have to place it over here on focus. Simply, this is the magnification. Now, if I want that image should be made at very far a distance, image is made at, okay, this was, okay, this is the magnification. Now image is made at distance D. Image made by the lens at, okay, this was basically the image made at infinity. So I am trying to say in this particular case, this is not the image at D, sorry. So if I say I have to see this object, I have to see its image, that should be bigger. But image should be at very far distance. Image should be at very far distance. Okay. With the help of this lens, I am able to see its image, which is bigger, but at very far distance. So we say its magnification will be this. But if you want to see the image at distance d, so we say this will be the image, okay, at distance d. So in this case, this will be the magnification. Okay, if you want to see the image bigger, if this is an object, you want to see its bigger image, but that is at distance d. So in that case, this will be the magnification. Next, compound microscope. Compound microscope is that microscope which you use in your schools. Okay, you have that two lenses. Okay, those two lenses you use in order to see the bigger object, to see the object bigger. See, in case of compound microscope, you directly remember we have got two lenses. This is objective and this is, we say, sir, eyepiece. Objective and eyepiece. If you place an object over here, listen to me very carefully. We say in this particular case, directly I say, this compound microscope also helps you to see small things large. Small things large. So I would say over here, listen to me very carefully. In this particular case, if the image is made at distance d, we say this will be the magnification in that case. This will be the magnification in that case. That is V naught by U naught, 1 plus d by f. D is the least distance of distinct vision. F is, we say, the focal length over here. And V naught by U naught. V naught is the position of the image. Sorry, U naught is the position of the object. V naught is the position of the image. V naught is the position of the image. Okay. So simply, guys, I say I use compound microscope to see small things bigger. So it will magnify the things. It will magnify the things. What is the magnification in this particular case? This much. This is the magnification in case of, we say, compound microscope. Okay. And in case of telescope, you directly remember this is the magnification at distance d. This is the magnification at distance d. So these will not be asked. Okay. But still I am basically telling you over here. Okay. Still I am telling you over here. Okay. And remember, this is the magnification in case of, this is the magnification in case of microscope. Okay. When image is formed at infinity. When image is formed at infinity, this is the magnification. When image is formed at distance d, this is the magnification. This is the magnification. Now, guys, listen to me very carefully. Next, we will be starting the, we say, modern physics. Now we will be revising the modern physics. Okay. So give me just 1 minute. I'll come. Just 1 minute. Okay. Now we are starting the modern. Now guys, let's start this particular chapter over here, that is dual nature of matter and radiations. Okay, listen to me very carefully. When it comes to the dual nature of matter and radiations, the first topic that we learn over here, that is energy of a photon. We say light is made up of small tiny particles which are called photons. Okay, so if I ask you how much is the energy of a photon, you say simply, sir, energy of a photon is h into f. H is Planck's constant, f is frequency. You can also say E is equal to hc by lambda. Planck's constant, speed of light, lambda is wavelength, okay, because f is equal to c by lambda. You can also say energy of photon is 2 into 10 raised power minus 25 divided by lambda. This is the energy of photon in joules. Okay, next. If I ask you energy of photon in electron volts, this will be the energy of photon in electron volts. 1240 divided by lambda in nanometers. Okay, this, so basically this is the energy of photon in electron volts when lambda is in nanometers. So if lambda is given in nanometers, you can use this formula to find the energy of photon. Next, you can find the energy of photon by this formula also. But when lambda is given an angstrom, you can find the energy of photon by using this formula also in electron volts. These are the 4 formulas of energy of photon. Okay, then we say energy of light. So we say light is basically made up of number of photons, n number of photons. So energy of light will be simply nhc divided by lambda. Now if I ask you how much is the power of light, so power of light is simply energy upon time. Okay, energy per second. In every second, how much energy is released? We say, sir, that is power. That will be nhc divided by lambda into t. Next, if we talk about the intensity, we say simply energy upon time into area, that is power by area. So this is the formula for intensity of light, nhc divided by lambda at. N is the number of photons, this is Planck's constant, speed of light, wavelength, time, and this is area. Okay, as simple as that, Next, photoelectric effect. What does photoelectric effect actually mean? We say if you have got a metal surface over here, we say you take a light source, photons will fall onto this metal surface. Because of this, we say electrons will be ejected from this metal surface. So when photons fall on the metal surface and electrons are ejected, this process is what we call photoelectric effect. Okay, now there is a concept of work function. Work function means minimum energy required to pull the electrons from the metal surface. How much should be the minimum energy? Like I say, for this metal surface, we say work function is 2 electron volts. Means if you have to take out the electron from this metal surface, you should give the energy of how much? 2 electron volts. Like for this metal surface, work function is 5 electron volts. Means if you have to pull out the electron from this metal surface, we say in this particular case, work function should be 5 electron volts. Okay, in this case, energy should be 5 electron volts. Now, this is the experimental setup of photoelectric effect. Like you have got a chamber over here, okay, tube-like structure, light source, light, and this is what we call the metal plate, that is cathode. This is what we call anode. When photons fall onto this metal surface, we say electrons leave from this and they move towards the anode. Okay, now here you guys directly remember one thing. What is that? That is energy of photon is equal to work function plus kinetic energy maximum. If you send the photon over here, that photon will give the energy to the electron over here. So that electron will use that energy to come out of the metal surface. Okay, so if energy of photon is 8 electron volts, so 2 electron volts will go in the work function. Okay, 2 electron volts it will use to come out of the metal surface. 6 electron volts it will use to move forward in kinetic energy. That's why we say 5 plus kinetic energy maximum. This is called Einstein's photoelectric equation. Okay. Now, if I ask you to make the graph between photocurrent versus EMF, okay, so we say it will be something like this. And the point at the potential, value of potential, where we say photocurrent becomes zero, current becomes zero, that is what we call stopping potential. So basically, when electrons move towards anode, we say current is produced. That current is what we call photocurrent. Okay, so we say this is the potential when photocurrent becomes zero. That's what we call stopping potential. Okay, now matter wavelength or de Broglie wavelength. So basically, de Broglie said everything in this universe has a wave nature and particle nature. If I say I have this pen over here, this pen has got particle nature, it has got wave nature. Okay, we say I can feel its particle nature. Now, if it is moving with some velocity, it will have wave nature also. There is a wave associated with it. And if I ask you, how much is the wavelength of this? That will be h divided by mv. H is the Planck's constant. mv will be the momentum in that case. H divided by mv. Okay. Now, my dear friends, listen to me very carefully. Listen to me very carefully. So we say de Broglie wavelength in terms of kinetic energy. So this will be de Broglie wavelength in terms of kinetic energy. H divided by under root of 2 mke. Okay. Then we say de Broglie wavelength for a relativistic particle. If there is a particle whose speed is equal to the speed of is comparable to the speed of light, which is moving with extremely faster speed, we say its de Broglie wavelength will be this. That is h under root of 1 minus v square by c square upon m naught into v. Charged particle accelerated under potential difference delta v. Its de Broglie wavelength will be h upon under root of 2mq delta v. Charge at rest in electric field. This is the de Broglie wavelength of the charge which is placed in the electric field. H divided by QET. All of these values you have to remember directly. If there is an electron moving in nth orbit of an atom, we say its de Broglie wavelength will be simply, that is nh divided by under root of 2m into 13.6. Guys, is this clear? Is this clear till over here? And most importantly, guys, like this session as soon as possible. I want everybody of you to like it as soon as possible. Liking the session is mandatory, very much mandatory. Everybody. Okay, now let's basically move on to the next chapter, that is atoms. This is not the fourth chapter. This is almost seventh chapter we are revising right now. So now when it comes to the atoms, okay, so the first model of atom was Thomson's model of atom. That is not compulsory. Rutherford's model I have also ignored, but directly I'll come on to the Bohr's model, in which question can be asked. So we say Bohr's model of atom says, so it was basically given in three postulates. Okay, first, what is the first thing it says? This is the nucleus at the center of the atom. Electron revolves around the nucleus. So Bohr said electron is revolving around the nucleus. We say means it's an accelerated motion. So means charge is accelerating, because electron is accelerating. Circular motion is an accelerated motion. Here charge is accelerating. Why? Because electron is accelerating. Electron has charge. So whenever charge accelerates, we say, sir, wave is formed. But here which wave is formed? Stationary wave is formed, which does not radiate energy. So Bohr said, if an electron moves in, revolves around the nucleus, it revolves around the nucleus but does not lose energy, radiate energy. Keep that thing in your mind. Okay. Next, Bohr's second postulate. So Bohr's second postulate defines the stable orbits. Listen to me very carefully. We say an electron revolves around a nucleus only in those orbits for which its angular momentum is nh by 2 pi. Now see, if I say you have got a nucleus over here, around this nucleus an electron is revolving. We say this electron will revolve only in that orbit in which its angular momentum is, we say, nh divided by 2 pi, in which its angular momentum is nh by 2 pi. Okay, and if n is 1, we say it will be h by 2 pi. If n is 2, it will be 2h by 2 pi. If n is 3, it will be 3h by 2 pi. So we say an electron can revolve only in those orbits in which its angular momentum is nh by 2 pi. Third, Bohr's third postulate says that if, let's suppose, an electron is revolving in the first orbit, if it wants to go from lower to higher orbit, from first to second, we have to supply the energy to this electron, then only it can make transition. And if it is revolving, let's suppose, in higher orbit, third orbit, and if it wants to make the transition from higher orbit to lower orbit, then in this case, it will lose the energy. It will release the energy. It will release the energy. Next, guys, listen to me very carefully. This is mathematical analysis of Bohr's model. If we say we have got an electron over here, listen to me very carefully. This is the nucleus over here. Okay. And we say its atomic number is Zd. Its atomic number is Zd. Now, my dear friend, this is the charge. Its atomic number is Z and charge here is Zd. Now, I am asking you the simple question over here. What is that? If I say an electron is revolving in the nth orbit, this is what? This is which orbit? We say, sir, nth orbit. Nth orbit. If an electron is revolving in the nth orbit. Okay. Okay. So radius is r. Now, it will have some velocity. How much is the velocity of an electron in nth orbit? We say that is 2.2 in 10 raised power 6 Z by n. Z is the atomic number. Like for hydrogen is 1, for helium is 2, for lithium is 3. Okay. And similarly, n is the orbit. So V is equal to V naught Z by n. Next, we say radius of an electron in nth orbit. Radius of an electron in nth orbit. So we say if an electron is revolving in this orbit, its radius is r, atomic number is Z. So how much will be its radius? That is 0.53 n square by Z. So you can also say r is equal to r naught n square divided by Z. This is the radius. Next, time period of an electron in nth orbit means if an electron is revolving in this orbit, how much time it will take to complete one cycle? That is what we call the time period. That is 1.51 into 10 raised power minus 16 n cube by Z square. This is the time period of an electron in nth orbit. Okay. Next. Okay. Now see, if let's suppose this electron is revolving in this orbit, okay, in nth orbit, we say it will have some speed, it has mass. So we say whenever any body is in motion, it will have kinetic energy. So here, kinetic energy of electron is Zd square upon 8 pi epsilon naught r. Now, if you have got over here, this is one charge, this is another charge. Now we say between these two, you have got, we say potential energy also. Whenever you have the two charges placed at certain distance, they will have potential energy. So these two charges will have potential energy. That potential energy is minus Ze square upon 4 pi epsilon naught r. So we say kinetic energy is inversely proportional to r, potential energy is inversely proportional to r. So potential is negative, kinetic is positive. And if we talk about the total energy will be minus Ze square upon 8 pi epsilon naught r. Total energy is also inversely proportional to r, that is negative. That is negative. Okay. So now, okay, these are the graphs. If somebody asks you to make the graph between energy versus r, this will be the graph of kinetic energy, this is the graph of potential energy, and this is the graph of total energy. Okay, rectangular hyperbola. Why? Because it is inverse, these are inversely proportional to r. Okay. Cool. Let's talk about this particular chapter, that is nuclei. Okay. So we say, if let's suppose I'm making the atom over here, we say at the center of the atom, you have got nucleus. Okay. So around the nucleus, we say electron is revolving. Now we need to discuss this nucleus in this particular chapter. Now see, if I say inside the nucleus, what are the particles which are present? We say protons and neutrons are present inside the nucleus. Protons and neutrons are those particles which are present inside the nucleus, Now, those particles which are present inside the nucleus are called, we say, nucleons. These are what we call nucleons. Now, my dear friends, listen to me very carefully. If I say, how do I represent a nucleus? If I say I have got a nucleus over here, I have to represent it. So we say I'll represent it with, let's suppose, X. X is the name of the nucleus. And I'll write over here A and this is Z. What is A? A means mass number. Mass number means number of nucleons. Mass number means number of nucleons. Number of nucleons means protons plus neutrons. Okay. And Z means atomic number, that is number of protons. Like if I say I have got a nucleus over here. It has got PPP, NNN. How many number of protons over here? 3. And how many number of neutrons? That is 3. So mass number is 6. Total number of nucleons. And protons, we say, sir, Z in this case is 3. Why? Because it has got 3 protons. And how to find number of neutrons? That is A minus Z. Rest mass energy. We say, if we have got a mass over here, because of its mass, it has got energy stored in it. So that energy will be E is equal to mc square. This is the energy stored in a mass. Okay. This is the energy stored in a mass because of its mass. Like we say, a body is in motion. Because of its motion, it will have kinetic energy. Similarly, because of the mass, a body will have, we say what? A body will have rest mass energy. And how to find that rest mass energy? We say E is equal to mc square. We say E is equal to mc square. Okay. Now, size of nucleus or nuclear size. You directly say this is the formula for size of nucleus. If I say I have got a nucleus over here, we say its size is, it has got more, this has got mass number 10, this has got mass number 5. Means 10 nucleons are present in this one, 5 nucleons are present in this one. Clearly you can see it has got bigger size. This also has got bigger size. So I can say, sir, radius is proportional to A raised power 1 by 3 over here. Directly remember. Why? Because we say volume is proportional to mass number. Volume means size. That is 4 by 3 pi r cube is proportional to mass number. So this is constant. R is proportional to A raised power 1 by 3. And we say R is equal to R naught A raised power 1 by 3. And if somebody asks you how much is the density of nucleus, so density of nucleus, you directly remember it is, we say 10 raised power 17 kg per meter cube. And this is constant for all the nuclei. Okay, now you have got binding energy. Now what is this binding energy? See, binding energy is that energy which is used to break the nucleus. Okay, if you want to break, see, if this is a nucleus, it has got mass number A, means A number of nucleons are present in the nucleus. And it has got atomic number Z. Z number of protons are present. If you want to break this nucleus, take these nucleons out. So we have to use energy. So we say, now further you write, sir, mass of Z protons will be how much? ZMP plus how many neutrons are over here? A minus Z. So A minus Z have got how much mass? A minus Z into Mn. So we say this is greater than the collective mass. Why? Because the energy you used over here, you supplied in order to break the nucleus, will be stored as the potential energy of the, will be stored as the mass of the nucleons. So if you want to break the nucleus, you have to supply the energy. That energy will not be wasted, that will be stored in the nucleons. That's the reason mass of the nucleons have increased. Okay. So we say the energy which is used to break the nucleus is what we call binding energy. That energy only is stored in the form of mass. And we say due to this mass defect will occur. How to find mass defect? We say ZMP plus A minus Z Mn minus M. This is final mass, this is initial mass. Okay. And you can find the value of binding energy also. Binding energy is delta M into C square. So this will be the value of binding energy that you can see. Okay. I hope this is also clear. I hope this is also clear. Okay, okay, okay. Now let's focus on this one. Now, if we make the graph between binding energy per nucleon versus mass number, remember one thing, guys. We say when it comes to binding energy per nucleon, it is proportional to mass number. Okay. We say binding energy is per nucleon, it is proportional to stability. Binding energy per nucleon is proportional to stability. More is the binding energy per nucleon, more stable a nucleus will be. As simple as that. More stable it will be. As simple as that. Now listen to me very carefully. Listen to me very carefully. If we make the graph between binding energy per nucleon versus mass number, okay, like binding energy versus mass number, we say binding energy per nucleon means stability. Okay, so more is the binding energy per nucleon, more is the mass number. Now the graph came out to be something like this. This is the experimentally verified graph. Now guys, on this axis we have the mass number. If I say I have got a nucleus, its mass number is 30. I have got a nucleus, its mass number is 170. So all those nuclei which lie in between this are stable nuclei. If there is a nucleus which has got mass number less than 30, means this and this 16, 15, these are what we call the lighter nuclei, and they are unstable. They are unstable. And the nuclei which has got the mass number greater than 170, they are also unstable, and these are what we call heavy nuclei. So what will happen over here? These two lighter nuclei will actually fuse together. They form a bigger nuclei. So this is what we call fusion. And this happens to gain stability, to attain stability. Now, if there is a bigger nuclei, it breaks into two smaller nuclei to attain stability. This is what we call fission. So here we say this is the concept of fusion and fission. Next, we have got a Q value of the reaction. Like we say, if A nucleus and B nucleus are converted into C plus D, and we say in this reaction, some energy may be either absorbed or some energy may be either released. This is what we call the Q value of the reaction. Okay. How energy absorbed or released in the reaction. Now, how to find this? We say, sir, Q is equal to mass of reactants minus mass of products, okay, into C square. Okay, you can write it something like this. Next, we say, guys, if mass of reactants comes out to be greater than mass of products, in that case, Q will come out to be positive. Means energy is released, it's an exothermic process. If mass of reactants is less than mass of products, Q value of the reaction will come out to be negative, means energy is absorbed. It's an endothermic reaction. It's an endothermic reaction. Okay. And one more important point is we also write Q value of the reaction in terms of the binding energy. That is, how do we write? Binding energy of products. I'll write over here. We say Q value of the reaction. We can write, sir, binding energy of products. Okay, minus, we say binding energy of reactants. Binding energy of reactants. Okay. Keep this thing in your mind also. Binding energy of products minus binding energy of reactants. Okay. Now let's move on to this important chapter. That is. Okay. See, everybody over here, is this crystalline clear? I want everybody of you to tell me in the chats. Everyone means everyone, guys. Is this clear? Guys, like this session? Okay. Now listen to me very carefully. Let's basically talk about this chapter over here, which is units and dimensions. Important chapter. Okay, from NEET perspective, you can expect 3 to 4 questions from this chapter also. So first topic in this one is physical quantity. We say a quantity that can be measured is what we call physical quantity, like length, mass, velocity, time. All of these are physical quantities. We say these are the measurable quantities. Next, non-physical quantity, that quantity which cannot be measured, okay, like goodness, love, hatred, okay. So these are not the physical quantities. Now, when it comes to the physical quantities, these are of 3 types: fundamental, supplementary, derived. Okay, and when it comes to the fundamental quantities, these are those quantities which are independent, on each other. Like we say mass, length, time, temperature, amount of substance, electric current, luminous intensity. So this is simple: kg mass, kg m second Kelvin. You can measure it. This is the assigned: kilogram, meter, second, Kelvin, mole, ampere, candela. Okay. Next. Then you have got the derived quantities. What are derived quantities? We say the physical quantities which are derived from fundamental quantities. Like we say force. Force is what? Force is mass into acceleration. Like you say area. Area is length into breadth. Force is mass into acceleration. So when these are those physical quantities which are derived from fundamental quantities. Okay. Next. Okay. Now listen to me very carefully. Dimensions. What does dimensions actually mean? Listen to me very carefully. We say it gives us an idea how many physical quantities are involved in how many fundamental quantities are involved in a physical quantity. Like we say velocity is displacement upon time. So how many displacements are present over here? One. So one time. So I can write LT minus 1. So this gives us an idea how many fundamental quantities are involved in velocity. One length and one time, that is in the denominator. Okay. Similarly, you can find for velocity it is LT minus 1. You can find for acceleration. Okay. For acceleration, how do we find it? So we say acceleration is velocity upon time. So for velocity, it is LT minus 1. This is time, so it will be LT minus 2. Similarly, for force, it is, we say, sir, mass into acceleration. Mass is mass. For acceleration, it is LT minus 2. Okay. So this is how do we exactly find the dimensional formula. Similarly, you can find all of these. You can find for all of these. Okay. Next. Now see, for momentum, this is the dimensional formula. For angular displacement, for angular velocity, angular acceleration, and frequency. You can see it over here. Now, you can take the screenshot of this. These are those physical quantities. These are those physical quantities which have same dimensional formula. Okay, all of these. Okay, like distance, displacement, radius, length, light years, wavelength, and these also. You can take the screenshot. These also will be having the same dimensional formula. Now, this is the dimensional for capacitance, for inductance. You can exactly see over here also. Then comes the concept principle of homogeneity. What does principle of homogeneity exactly say? Principle of homogeneity says that we cannot compare two different physical quantities. Like you have got 4 meters plus 2 kgs. It is illogical. We cannot add 4 meters with 2 kgs. It is not possible, wrong. 3 meters minus 2 seconds, not possible, wrong. Or we say 5 kg is greater than 3 meters. This is also wrong. But you can say 8 meters plus 7 meters is 15 meters. This is correct. Okay. So you can basically compare same physical quantities. You can compare the same physical. Two quantities must be having same unit dimensions which can be added or subtracted, equated. This is the principle of homogeneity. But remember, you can multiply two different physical quantities, like force is equal to mass into acceleration. Mass is one physical quantity, acceleration is different. Okay, you can multiply. Significant figures, important. So we say, let's suppose I say I have got a question over here. I have got a question over here. We say 4, 5, 7, 8, 9. I am asking you how many significant figures are in this number. So there are rules which needs to be followed. Okay. The first one is all non-zero digits are significant. Like 56 had got 2 significant figures. This has got 1, 2, 3, 4, 5. 5 significant figures because all non-zero digits are significant. All zeros between non-zero digits are significant. Okay. All zeros on the left side are not significant. If there are zeros placed on the left side, they are not considered to be significant. Power form are not considered to be significant. Like if I say over here, we say 4 into 10 raised power minus 10. So we say here it has got only one significant figure. This is not considered to be significant. Trailing 0 after decimal is significant. If I say 5.8.00, it has got 3 significant figures because these are also considered to be significant. Okay. Next. Okay. Measuring instruments. The first measuring instrument is we say meter scale. Okay. We use these measuring instruments to measure the length. We use these measuring instruments to measure the length. Okay. As simple as that. Just a second, guys. So this is the meter scale. This is the meter scale over here. Now listen to me very carefully. How do we take the reading by using meter scale? That is important. Now see, guys, if we have got this meter scale over here, okay, we say we have to measure the length of this rod. We say length reading here will be main scale reading. That is this main scale reading plus minus least count. Least count is the minimum measurement we can measure, minimum length we can measure with the help of an instrument. And when it comes to the least count of this, that is we say 1 mm. 1 mm we can minimum measure. If I say something is less than 1 mm, we cannot measure that with the help of the meter scale. How do we take the reading over here? That is main scale reading. For this, it has crossed, we say, sir, 4 mm. So main scale reading in this case is 4 mm. Then we say plus minus least count. For meter scale, it is 1 mm. So it will be 1 mm. Similarly, for this also, it is plus minus 1 mm. It is 4 plus minus 1 mm. For this length, it is completely coinciding with 5 mm. So its length is 5 mm. This was basically the meter scale. Let's talk about vernier calipers. So if you have got something which is less than 1 mm, so you can measure that with the help of the vernier calipers. Okay. Like my dear friends, you have got this scale, main scale over here, and then you have got vernier scale over here. So in vernier calipers, you have got 2 scales, main scale and vernier scale. Main scale and vernier scale. Okay. Now, how do you take the reading over here? Like this is, we say, sir, vernier calipers. Here, what is the least count of vernier scale? That is 0.1 mm. Remember it directly. What is the minimum measurement we can measure with the help of the vernier scale, vernier caliper? That is 0.1 mm. Okay. Now, how to take the reading over here? I'll tell you. I will tell you. See. So we say when it comes to this one, okay, length of the rod. If you have to measure the length of the rod by using this, what you will do is length of the rod will be simply main scale reading plus least count into vernier scale reading. I'll write over here. See. We say in this particular case, we say reading will be main scale reading plus vernier scale reading into, we say, sir, least count. See. If let's suppose there is a rod, you have to measure this rod. Now, main scale reading will be simply this rod has crossed, we say, sir, 1 mm. So I'll write over here. This is 1 mm. Okay. Then plus vernier scale reading. Vernier scale reading means, or you can also say coincide reading. That is, We say here in this particular case, 3 is coinciding with 4. 3 is coinciding with 4. So if 3 is coinciding with 4, so vernier scale reading you will be taking as 3. 3 over here. Okay, 3 over here. Now, my dear friends, listen to me very carefully in this particular case. We say if 3 is coinciding with 4, multiplied by least count, that is 0.1. Okay, so this will be simply 1.3 mm in this particular case. Okay, this is, see, simply what you are supposed to do is, we can say you have to check this, it is coinciding with what. Okay, it is coinciding with what, and then we say what is the main scale reading over here. What is the main scale reading over here? Just a second, guys. Is this clear to each and everyone? Is this clear to each and everyone? Guys, let me know in the chats if this is crystal and clear to each and everyone. And if you have not liked this session yet, I want everybody of you to like it as soon as possible. That is mandatory. Okay. Now, error analysis. Error analysis. The first one is absolute error. This absolute error is, we say, true value minus measured value. Okay. True value minus measured value. Let's suppose there is a rod. Okay. Its true value is, we say, sir, 5 mm. Okay. And you measured it, its measured value came out to be, we say, let's suppose 3 mm. Can you tell me how much is the error that you made? 5 minus 3, that is 2 mm. Okay. Now let's talk about the relative error over here. Relative error. We say if absolute error is 1 centimeter, and my dear friends, error came out to be, listen to me, if let's suppose absolute error is 1 centimeter and true value is 5 centimeter. Listen to me very carefully. Listen to me very carefully. And here we are taking an example in which we say delta L, that is absolute error, that is 1 centimeter. And I am saying, let's suppose true value of the rod is 5 centimeter. In 5 centimeter, you are getting 1 centimeter error. So means error is bigger. Error is bigger. So here, if let's suppose error comes out to be, absolute error is 1 kilometer and true value is 6400 kilometer. So in 6400, you are getting 1 kilometer error. Here, in 5 centimeter, you are getting 1 centimeter error. We say here error is bigger and here error is smaller. Now, we have to check basically how much error is bigger. So we use basically a relative error concept. So we say absolute error divided by true value, delta x divided by true value. So this tells us how much error is bigger compared to the true value, that is the relative error. And if we talk about the percentage error, simply multiply this with percentage, so you will get the error in percentage. Like guys, I say delta L is 1 kilometer, LT is 6400 kilometer. So if I ask you how much percentage error is over there, you say, sir, this will be delta L divided by LT into 100. This, okay, 1 by 6400 into 1, that is not even 1%. So error is very small. Error is very small. And in another example, true length was 5 centimeter. This measured length, absolute error was, we say, 1 centimeter. Can you find relative error? So 1 by 5, that is 1 by 5. So percentage error in this case will be 20%. So that's what I was saying. So error in this case is extremely large. Okay. Okay. In kinematics, I would request you to basically focus on these things. Now see, what is that? In kinematics, I would basically request you to focus on these things. Let's suppose we have got a car, not this one, next one. Yeah. Ratio of total displacements in 1 second, 2 second, and 3 second. Let's suppose I have got a car over here. Okay. It started from rest at t is equal to 0. At t is equal to 1 seconds, the car, let's suppose, reached over here. It covered x distance. At t is equal to 2, the car is over here. At t is equal to 3 seconds, the car is here. At t is equal to 4 seconds, we say the car is here. Now, my dear friends, listen to me very carefully. Listen to me very carefully. If I am saying that in 1 second, it is covering the distance, we say, sir, x. Okay. In 2 seconds, how much distance displacement it has covered? If this is x, this will be 4x. In 3 seconds, how much displacement it has covered? 9x. In 4 seconds, we say it is 16x. Now, can we find the ratio? Ratio of displacement in 1 second, in 2 seconds, in 3 seconds, in 4 seconds. It's x, 4x, 9x, 16x. So it is 1 is to 4 is to 9 is to 16. So this will be the ratio of displacements in 1 second, 2 seconds, 4 seconds, and 6 seconds. And we say 4 seconds. Next here. Ratio of displacements in 1 second, 2 second, 4 second. Okay. If I say, let's suppose our t is equal to 0, car is over here. And in this case, there is a condition. Condition is initial velocity of the car should be 0 and acceleration should be constant. Guys, see, listen to me very carefully. So we say I have got a car over here. This is the car, okay? It started from rest. At t is equal to 1 seconds, the car reached here. T is equal to 2 seconds, the car reached here. T is equal to 3 seconds, the car is here. And t is equal to 4 seconds, the car is here. Now, my dear friends, listen to me very, very, very carefully. I am saying that. So in first second, it has covered this much of displacement. In second, it has covered this much of displacement. In third second, it has covered this much of displacement. So that's what I'm trying to find. Ratio of displacements in first second, second second, third second, fourth second. It is x is to 3x is to 5x is to 7x. So this is the ratio of displacements in first second, second second, third second, fourth second, this much. Okay. Okay. Let's suppose if we talk about the position time graph over here. If there is a car, if this is a car, okay, which left from this point, okay, it is moving with, it's at t is equal to 1, it's at 1 meters. T is equal to, it's at 2 meters, okay. If we make its position time graph, that will be something like this, straight line. Now, if we find the slope of this position time graph, slope will be simply tan theta, and that will be simply perpendicular by base, that will be simply delta x by delta t. Now, directly remember over here, slope of position time graph gives us the velocity. Slope of position time graph gives us the velocity. Okay. And if somebody asks you, let's talk about velocity time graph. Sir, if you make the velocity time graph over here, we say if you find slope over here, slope of velocity time graph gives you the acceleration. Remember it directly. Okay. And area under velocity time graph will give you, we say, sir, displacement, will give you displacement. If you find the area under velocity time graph, that will give you displacement. Okay. Okay. Let's talk about this laws of motion chapter. Let's finish this in next 10 minutes, okay? Now guys, see, when it comes to the laws of motion, here we define first law of motion. What does it say? Everybody wants to keep its state of rest or uniform motion until it is acted upon by some external force. What does that mean? If I say this is a body which is at rest, if net external force on this body is 0, we say the body will remain at rest forever. Okay. And if I say there is, we say, sir, another body which is moving with a constant velocity. If net external force on this body is also 0, we say the velocity will remain constant. Okay. If I say, my dear friends, in this case, if there is a body which is moving in certain direction, we say in this case, if net external force is 0, we say direction will also remain same. This is the Newton's first law of motion. Okay. Okay. Then comes the second law of motion. If I say I have got a body over here which is moving with a velocity v, if you apply the external force, we say, sir, after some time its velocity will be v dash. Okay. Now, my dear friends, on applying the external force, we say its velocity has changed. If I ask you, sir, here its momentum was, sir, m into v. Here its momentum is, we say, sir, mv dash. So can I say in this case momentum has been changed from mv to mv dash? Yes. Now, my dear friends, tell me one thing. Tell me one thing. So by applying the external force, we say its momentum has been changed. So that's what Newton's second law say, F is equal to dp by dt. On applying the external force, its velocity will change. Because of the change in velocity, we say momentum will change. Momentum will change. Now, there is a forces in mechanics. The first force is weight. If you have got a body over here, we say in downward direction, there is a force which will act, that is mg. Okay. Like if you place this body over here, in the downward direction, it will act, that is mg. If this is theta, this will be theta, this will be mg cos theta, and this will be mg sin theta. These are the components. Okay. And we say it is a gravitational pull by earth. It is vertically downwards. Next is normal force. When two bodies are in contact with each other, they apply the force on each other. That is what we call the normal force. This is the normal force. So in the downward direction, on this table also normal force will act. On the block also normal force will act. Okay. Next. Then you have got tension. Whenever you have a block attached with a string, we say in that case tension will act. Here in the downward direction, mg is acting. In the upward direction, tension is acting. Okay. Now see, if you have got a system, let's suppose something like this, and you are supposed to find the acceleration of the system, I will tell you how do you exactly find. We say acceleration of this system will be simply that is net external force divided by net mass. Net external force divided by net mass. Net external force in this case is how much? See, we say in this case, in the downward direction, we say 5 into g will act. 5g means 10, that is 50 Newton is acting in the downward direction. Here we say, sir, 30 Newton will act in the downward direction. So net external force will be 50 minus 30 divided by net mass. Net mass is 5 plus 2 plus 3. So this will be the net mass in this particular case. Okay. Next you have got over here, find the tension T2 in the string. Find the tension T2 in the string. Now see, okay, this is the question, guys. Here you find the acceleration first, net external force. Net external force is this, net mass, this plus this plus this. Then you can basically find the tension also in this particular case. Okay. What is I guess that's it for today, guys, huh? That's it for today. I guess that's it for today. So there are few topics left that I will be covering in the next class. But there is a very important session that I will be basically covering in the next class. That is over there. Guys, listen to me very carefully. Come, see, I will tell you. So there there is a session on the channel that I'll be taking tomorrow at 1 p.m. That is sure short concepts that you can expect 100% in the next, we say in your NEET 2024. So tomorrow I'll be taking with the problems also, the concepts plus problems, but speed will be less. Today my speed was basically fast because I had to revise all of these chapters. Okay. So tomorrow I'll be taking all of those short topics, which you can expect in the NEET. That's for sure. Yes, practice session will be there. Topics plus, we say, sir, we say questions plus. Tomorrow, I'll write over here. Tomorrow, I will be taking short questions plus concepts. So I'll be explaining the concepts plus questions, which you can 100% expect in your NEET. Okay. So do come in the tomorrow's session at 1 p.m. that is scheduled on the channel. I want you guys to go and smash the like button over there. Go and smash the like button over there. Okay, let me show you on the screen. Like, my dear friends, we say, I'll write over here, Unacademy NEET, Unacademy NEET English. This is the channel that we have. Okay. Now, guys, see, there is there is basically a session scheduled for tomorrow. Yes, this one. This is the concept that I'll be taking tomorrow. This is the concept that I'll be taking tomorrow. That is sure short concepts. Okay. This one, sure short concepts plus questions. I want you guys to go and like this session as soon as possible. Here we will be basically explaining all those concepts which you can expect in NEET 2024 in a concise way, plus questions out there. Okay, so I'm ending this session right now. So thank you so much, guys, for this. See you guys in the next session. Till then, bye bye and take care. Okay, I want you guys to comment down below how was the session, everything and all. Okay, and my dear friends, most importantly, everybody of you, I want you guys to like this session, everybody out there, because liking the session is mandatory. Liking the session is mandatory. Okay, like this session as soon as possible, and then I will leave. Okay, do comment afterwards. Okay, guys. Okay, yeah, I'll be sharing the PDF in the Telegram channel. You can also join my Telegram channel, that is t.me/Yawar Manzoor. t.me/YAWARMANZOOR. Okay, over there I'll be sharing the PDF. Okay, so guys, thank you so much. We are done with the maximum topics over here. So the rest of the topics which I feel I need to discuss, that will be in the tomorrow's session. Okay, I'll write over here, tomorrow's session is very important. Very important. 1 p.m. 1 p.m. All the sure short concepts, everything I will be discussing over there. Everything I will be discussing over there. Okay, so thank you so much, guys. Do comment how was the session once I end the live stream, everybody.